So hi everyone, thank you for being here today with us. So I'm Manuel Serrano. I have been organizing or chairing this workshop this year. So it's a 10th edition of Rebels, so already pretty old. So it's glad to be active and productive. So this year, maybe we have received slightly less submissions than previous years, and I think we have been fighting against, or we have been struggling with the deadlines, which were not so convenient. Just middle of summer, it's really inappropriate. So I guess that for the following year, we will try to improve on that. But anyway, all the submissions we have received were quite in the focus of this workshop, so quite interesting, and presenting interesting ideas. So clearly, we have received little numbers of submissions, but all were interesting and probably engaging interesting discussion. So this is why probably we will have an interesting workshop. And once again, I welcome you here in Portugal and for this workshop. So thank you so much.
Greetings, Rebels. Welcome to the first session. So I will be another piece of furniture that you will encounter today. I'm the session chair for the first one. So we start, of course, with a keynote, and the keynote today is Elisa, and it is my utter pleasure to introduce her. So Elisa González-Bois, she's a professor in Belgium, in the Free University of Brussels, and she has been repeatedly publishing on exactly this topic of, agent-based reactive system. So if you've never heard of her, then well, probably listen first to the keynote, but then do Google her up or DBLP her up, because she has written quite some interesting pieces on this topic. And she's also head of the DISCO group, which is about distribution and concurrency. Thank you very much. So the floor is yours, and do your thing.
Yeah. Okay, so this is a workshop, so you can interrupt me at any time and ask me questions. I will try to do a brief idea of what I have been working with my group in the DISCO, and I will do two zoom in so that I don't bother you with all the details. But let me explain you a bit how it all started, and I see the slides, good. And it all started 20 years ago, yeah, that's how old I am. In computer science, and I was I'm originally from Barcelona, Universitat Politécnica Catalunya, and I went to Brussels to basically do some research for my master thesis about basically a programming model for ubiquitous computing. That was something big by then. It was this vision of Mark Weiser that has postulated earlier before, but now the hardware was getting there that we could start looking into how to really build software for those systems. So my supervisor then, my master thesis supervisor said, in an ubiquitous context, actually asynchronous communication suits better. Why do you don't implement an actor-based language? And I was like, a language? Seriously? So I come from a systems background, so I had always been programming in C, looking at databases, networking, and I had not even considered the fact that I could become designer of a language. I mean, that was mind-blowing for me, a different philosophy there than where I came from. So my own language, I guess that with the 4-5 months that I had to be there, he kind of knew that maybe it was a bit overwhelming. I had only written a compiler before for a course. So then he said but we have a couple of people running around in the lab, which are already taking a small language that we have for education called Pico from later my supervisor, Theodon, and trying to put it into, re-implement it in Java, because there is this promise that then you could run anywhere, including wireless communicating devices. And so that's when basically I first learned about the language. It was a continuous in-passing style interpreter written in Java. There were a couple of people looking into writing communication for this based on SOAP, some technology of objects over web. And my supervisor said, read this paper about Gul Aga and try to see if you could basically merge this into the objects of Java Pico. And that's how I ended with my master thesis. I looked it up, and I'm not very proud of the syntax or how it looks like, but it was my first attempt at working in basically building a programming language or a programming model for ubiquitous context. And then, yeah, it was not really evident to me that I could live from doing research. I had a wonderful time, but how do I get food? And I couldn't find a job in Belgium because I didn't speak Dutch. I spoke French, but not good enough to be hired. So I went back, and I went back to my system programming. So I was working from UPC, developing tools for IBM DB2 on those days. But yeah, there was something in me that made that holidays, talking to people, make me start it all over again. So here we are, a year and a half later. I come back 2005, but there is not like 2 master students. They already have a group. And my supervisor, Theodon, with them, like brainstorm, like what can she be looking in within the same topic. By then they had developed ambient talk built on those ideas, and it's like also an actor-based language. They already had a full-blown distributed model. It's like, what about if you explore how to handle failures there in ambient talk? And I was like, ambient talk? What's that? It's like, well, this project grew. We found some Catalan code comments, very bad. You should always write in English. It's like, wait a second. Till now, I still have not found this code. I tried for this presentation, but I did not find. So I think it's not true, but OK. So I joined the group, and then I started basically looking into how we could model failures in an object-oriented way, because we were trying to program distributed applications. We were very dynamic. So you were peer-to-peer, you will meet on the devices, and then start collaborating. So Ambient Talk, they had been working on marrying events with objects. That's what they were doing. And it was a superset, so it was based on the principles of ambient-oriented programming. You have a superset of object-oriented programming, which is specifically geared for distributed computing, but especially for these mobile networks. Why they were so special? Because you didn't have any infrastructure, fully decentralized, and there were a lot of failures. So by then it was a bit niche, but by now, like having decentralization and having to deal with failures, it's quite normal, not only in mobile networks, but in any modern distributed system you encounter, from cloud to IoT. So, okay, if you look at the programming model, you had to basically discover services and ask application requests, and that will be modeled with asynchronous message passing, which have a special operator. You know that in Scala, they use like as well special operators. On Erlang, this was the one for us in Ambient Talk. You will also have events to follow up on your request. So if you sent an asynchronous message, you wanted to get the return value, again, there was an event model, the resolution of a future. Some of you might know it as promises. And then you would apply a closure when this event happened. And then we had events to react to the fact that we were in an ad hoc environment. So discovering services, whenever discover, you get a reference, so object reference to another device, or reconnecting and disconnecting when you lose network failures. So to give you a feeling of how it look like, this is a little ping pong application. So on the left-hand side, you have a phone in which it's exporting an object that has a ping method. So when it receives that request for the ping, it will write ping on the console and send back the symbol pong. And this object could be exported with what we call a type tag. So think about it as an empty Java interface. And then that makes that you will put it on the network. So basically, the language had facilities like PubSub built in. At the other side, what you have is like, OK, you define the same type. And whenever you discover this type tag, then this closure will be applied, and you will get an object reference to that device there. So then you could start doing like requesting services like the ping. I want that it's a future message, because when I get the value, I then receive the ping. So in this model, basically what we had, it was clearly event-based. You have all these callbacks for different types of events. And the data was stored at an owner. So in this case, there was this object, ping pong object. And all operations will happen via synchronous message passing. That was good. It decouples devices. It allows you to build things. But all operations will be executed, let's say, at the owner. So I was trying to reconcile then failures and their effects. And that's where one of the things that I did that are in the trunk of the language it's basically integrated with leasing. That allowed me to solve 2 problems, because on these references that we had here, it allowed me to basically do some cleanup. I could say, like, for 10 minutes, this connection is valid. And after this time, I can do some garbage collection at this site. And at that site, the sender of the request will be able to distinguish between intermittent and permanent failures, when is a connection needs to be considered that you would drop. And that's what they did. So we integrate the failures in the model so that it will be a bit easier for the programmer. So that's how your references now from objects in different machines will look like, from connected to disconnected to reconnected, and sometimes we will just cut them when they expire, and from here on they are useless. So there is a new type of event coming in, the expiration, very important at that site to do garbage collection, whenever this object is no longer locally referenced, and very important, it could be triggered at that site to react to permanent failures, basically. That was the idea. So that was part of my PhD. And then I procrastinated a lot. I don't know if that's allowed nowadays in programs, but what does it mean, procrastination, since the very beginning? Well, we wanted to build things, right? There were all these devices. At the beginning, the devices were just laptops. And the demos like there, you don't see it a lot, but it's a Portal game. The performance was not our goal, but it was quite horrible. I had to animate the demo, so we record the demo. And then with the movie, I had to animate it because otherwise the ball was so slow that it was embarrassing. But it's distributed, right? So a ball could go from my device to there. We'll be jumping around. Then luckily for us, in 2009, nicer devices come, easier to basically target them than just having a Java VM with Android. So then we could really start thinking about more application case. So it was a lot of fun to, on Fridays, have these hacking sessions. Then we also had supervisors giving us money to buy devices. That's also important. We had money to buy devices. So I started going with some of my colleagues to hackathons. This is like distributed paint drawing. This is a Pong, a real one, so not this one. You can play it, and my students are still implementing this as an exercise now at class. Pong, that they pay us to go to London to continue programming on it. So, and when you are building all these applications, actually we had built a model with objects and events, where the main abstraction when these object references crossing devices. But I realized actually that in many times, what I needed to implement these applications was to share data. And basically, this is another example. Imagine an imaginary country where they want to do elections, called Catalonia, doesn't exist yet. And then you want to build this voting system where you want to represent basically what's going on. In ambient talk, we had objects were passed by reference, but you could also have something called an isolate. And an isolate will be an object that was passed by copy without its lexical scope. So then basically that was interesting, because from a point of view of the model, that means that you could do operations execute locally that will faster, so it will increase the availability. And also you could have different copies, replicas, so increase, like you avoid a single point of failure of a reference where you always need to go to the owner of the data, right? But the problem is that, consistency was left up to the programmer, because rather than building it in, it was by design that we will always try to be available and partitional tolerant. And if you know a bit about distributed systems, there is this big famous theorem called the CAP theorem that says that you cannot have availability, partitional tolerance, and consistency. So at this moment, consistency was left to you. So every application, you will have to basically build it over and over. And that's when it's like, well, but we could build some basically replicated objects, right? And what do I want? I want abstraction that developers can customize conflict resolution, because if you have replicated objects and you have concurrent updates, you will need to deal with what do you do when they are conflicting operations or updates. And here is like my supervisor, like had already talked to me or given to me at some point a paper called the Bayou Architecture, Support for Data Sharing Among Mobile Users. And this was a paper by the mayor in the context of actually more like the mobile adult networks kind of world, okay? But in the databases kind of community. But I found this very interesting because I'm sorry that the font size maybe is not big enough for the back. But basically what Bayou allowed is that you could have like a number of database services that you could connect from different locations because the users were mobile. And then you could always issue an update. And with an update, this is an example from the paper, so very old, it's from 95. It says I want to do a meeting between 10 and 60 minutes for project meeting with Kevin. And then it had this dependencies check that actually was kind of checking if the update will be, what are the conditions so that the update can succeed. So basically, it will select the key from the meetings table to know that there was no other meeting already there. So the result, the expected result, the expected invariant of the application was to be that this will be empty, so that then you could add this record. The thing is, like, if there will be a concurrent update and there will be a problem and this doesn't hold, you could have a merge procedure that will try to give the means to the developer to resolve this conflict. And here, basically, it is still, as I said, it's in the databases. It is expressed in terms of SQL queries. So it will check there's a conflict, and if not, select another time. And if don't, give the bug this time. Otherwise, it will have to retry. So this is very interesting because I have application-specific, basically, conflict resolution. But I didn't like that you are exposing this merge procedure directly because they are very difficult to get right. And you also need to ensure that then the two replicas will converge. So it's like, yes, I want something like this, but I don't want the explicit merge. And that's why when basically there were a group of people that they had already been thinking about that. And I found super cool the work of Shapiro et al. From CRDTs that came in 2011, because here, behind the abstraction, they will, for a number of data types, they will already give you by default a merge procedure. So you as a programmer can basically get a data type, and then the implementation takes care by design following some mathematical properties that you couldn't have the conflicts. So that's nice. I thought this is a nice abstraction to give to the programmer. Basically, they had already worked out all the merge procedures for a number of data types. There were flags, there were sets, there were registers, there were a number of data types there. Okay, cool. So this is a specification, for example, of what it's called a state-based increment-only counter. So what I would need for my voting system of my imaginary country. And then basically this is how it would look like in ambient talk. So you would, you don't need to know a lot about the specification, but basically it's using a vector of increments on every position will keep the increments of every node in basically that it's participating in, or every replica in the network. And then when you increment, you actually increment the position of your ID on that vector. So when you merge, basically what you are doing is taking the maximum for so the vector that comes to you from the network from the one that you have. Okay, that's nice. This paper didn't talk anything about the distributed aspects. I want to use this in distribution, but okay, it's good. I know how to do that. We know from ambient talk. So basically I can just like put in the distributed aspects, and how would we do that in ambient talk? You will define a trait, an object, where you basically will pair everything that you need to discover the replicas and what to do when they are not online and so on. That is something based on the event-based model of ambient talk that we could already quickly hack in. And that's what is going on here, right? So when you want replicas to sync, this is the sync method usually from that you will propagate the update. So it just does a broadcast of the merge function getting your own information. So serializing will mean to send over this vector. Broadcasting, well, I just had to keep basically a connection to all replicas. And how do you model this in ambient talk would be an object reference. that I will use like the same kind of events. I will export self so that everybody can find this replica, and whenever I will find a replica with the same name, then I will just add it in my list. That's needed so that then at every broadcast message, I can just forward the message. That's what you see here. There was a lot in this ambient talk language, like reflecting was built in. So basically, this was a special operator because messages were first class to then say, this message I get here, send it to the receiver, which will be in another machine. That's nice because I have my RDT, and by importing the trait, I get my distribution, basically. But I was not done, right? Because basically, I have a number of data types, but they are not application specific. I have sets, I have registers, I have counters, I have a number of them. And there was a lot of people thinking about how to design these merge procedures, or there was also like how to make operations commute if you take another branch of CRDTs, so that you can offer it as an abstraction, but you cannot customize the concurrent semantics to your application. You always need to take a different data type. And if you don't have a data type, either you create it or you wait that there is another PhD student who comes up with the tricks. So that's one thing. The second thing is like, I want to support application invariance. So some of these, it's not only about that the state converges, sometimes you also need to uphold some invariance, and this might transcend one data type. Second thing is like when you don't have a CRDT ready to go and you start building, how does the developer know that it's correct? So in this sense, correctness a lot of times is associated with converge. So how do you know that it will eventually, all the replicas will be in the same state? Because yeah, for the CRDTs, there is a lot of smart people who have already worked out the proofs. So they publish the paper with a manual proof, or in the old days now it's going more mechanized. And they know that this is correct. But the moment that you start extending it and making it to your application, you need to provide some means of how are we going to make that the programmer can be sure that its modified design is still correct. Composition. So if you think about object orientation, you always immediately think about having composition by means of nesting objects, etc. And this was also like how I am going to do this with these replicated data types. And finally, because I always keep the touch with the hardware, I was looking as well to more Internet of Things applications. This one ran on low memory, low power devices. So how do I feed this nice research, which is meant for geo-distribution, into environments which are dynamic, like I had with the mobile networks, but that they are memory and network constrained? So there are a lot of questions that I have been looking with my group. And then what I will do is to zoom in into one of these questions, because obviously I cannot start here, like going over all. There is a lot, and some of these questions we are still working, our group and also the community. Okay, I will do a pause for drinking. I don't know if there is something already on the ambient talk part before I delve into the first zoom in with the replicated data types.
What is left of all the things you have done with ambient talk? Is it still active? Is it,
I use it for teaching, distributed programming. Many of the things that I use the language as a vehicle to basically bring on the concepts that are now being in research or that they are established. But it's like a vehicle now for teaching.
and the core concept of this language, have they been reused in other
Well, so there are some aspects of the language that have percolated. For example, there was a lot of work on the reflection aspects, so that you could change the language within the language, because we needed this. There were a group of students, and each working on a topic. So what you want is a small core that then you can adapt for all these experiments. And for example, this line, then with Tom Van Kutsem working with Mark Miller, got into the ECMAScript proxies. So actually the mirrors, intersection mirrors of ambient talk are now applied to the proxies, yes. So this is one of the most successful transfers that there is within all the basically research within because it was a big group. I think that we were about 10. At some point, there have been, I think, 10 PhDs being produced, but Wolf is not here, so he probably keeps account. I was only exploring failures, so I talk about my side, but there were many people there, including Christoph, which is also here, and you already saw his hand on the phone. Okay, so let me do the delve in then. I want to talk to you about this quest to have this basically general abstraction, because I want to keep into account the application semantics. And this is basically work that I started with my PhD, Kevin, and at some point we ended up going to Carla and Nuno to join forces to get this, basically to help us get it streamed out, and we collaborated with them for a couple of years on this. So the idea is like you want to invite these new data types for your application, but following the mathematical properties of CRDT sometimes is very hard. And we also, or personally, I also didn't know what can you express, or that as a CRDT, what kind of things will be able to be expressed as CRDT, and which ones we will not be able to find tricks so that basically the state converge. That was the idea. I want to have built any data type, so go more general purpose, taking into account application semantics, but trying to remain basically available as CRDTs. And that's how we came into the explicit, consistent, replicated objects. So the idea was to build a general purpose RDT. Initially, that could be like CRDT, so basically they provide state conversions. But I didn't want to give directly RDT. I wanted to start with a sequential data type, because that's well understood for programmers. We all have this in computer science. And then, like with the idea of Bayou, it's like, what if we could add a distributed specification that will say how does the sequential data type has to behave when they are concurrent updates on the operations. That was the idea. And then I want to get back a replicated data type, which as much as possible avoids having coordination. That's what CRDTs do. You can update them offline. They have a built-in conflict resolution mechanism that does not rely that all the replicas have to be online to agree on a value, which is the old way of doing it with the databases and a strong consistency. But yeah, there are times that it could be that basically that's not possible. And when it is not possible to avoid coordination, then we will go into using logs. So it's a hybrid data type, because the idea was that you want to provide an abstraction that basically hides as much as possible as the difficulties of resolving conflicts. That's the idea. Okay, whoops. So we move from ambient talk, dynamically typed language, inspired a lot by Smalltalk, Lisp, the E language, well, Self, etc. And we go into Scala. So basically, that's my fault. I said, I think that the Scala for this kind of work could be better than Erlang, what he wanted to do. And then he went to Scala, full types started falling. I have learned a lot about this. So what do we have? We have a sequential data type, here written in Scala. We will have a domain-specific language that will help us, written in Scala, will help us with this distributed specification. So the SALT, to say what are the concurrent semantics that this application needs. And then we get a replicated data type. Let me go over the two components so that you understand what is the idea. So first, if you want to do something like an add-wins set, that's a well-known CRDT. It's a set in which if you have a concurrent add and a concurrent remove, the add will win over the remove, because the thing is like they don't commute, so one of the two will have to win. So you have a sequential implementation in Scala. You basically leverage into the data types that the Scala had. Like I said, you need to provide the adds that just as it provides you a new set with the element. The remove will remove it, and then it checks the contain. So basically, it's quite close still. The idea is to remain quite close as possible, as close as possible as to the specifications of CRDTs, while being a real language implementation. And then there will be the distributed specification. What does this mean? Well, what you see here is a small DLS on top of Scala. First of all, what I want is that I will have to specify what are the effects of each operation, and that was done inside the post condition. So the post condition of add will take the old state and the new state. It will check if the element is in the new state after you do an add. We need this relation. I forgot to say it. And then, well, it has to do a copy of the old one to check that it is that it's the only element that remains there. And then you have the post condition of remove, which basically will be the opposite. It should not be there, and then check in the copy step. Well, you see, this is the domain-specific thing. This will be an AND. He leveraged it on using Scala meta. And the important part for us is here, because that just is telling the effects of the operation, but the invariant is what will define the concurrency semantics. And that means it's an invariant on the add operation, and then after checking all concurrent operations with that, what needs to happen is that the element is still in the set. So if you would have a concurrent remove, when this invariant comes, then you had to make sure that this is done. So what's going on here? You start with a sequential implementation, and you add an invariant to express basically an add wins. If you want to remove wins, I don't need to go and create another data set. I don't change my sequential implementation, but I need to change my invariant. I don't want that it's an invariant on the add operation. I want it on the remove. And in this case, after checking all concurrent operations, the element should not be there. So if there was a concurrent add, the concurrent add should lose. That's basically the idea. Are you still all with me? Because that CRDT is going, phew, okay? I know that maybe some of you are not in the data. Yes?
Yeah, I'm not totally following, because what I see on the left-hand side is something rather abstract, that just describes you a kind of interface, but no implementation details, because I don't know what is behind this
yeah.
you said.
Yes, this is a wrapper actually around this that will then have the conflict, the algorithm for the replication.
But where is implemented the algorithm? In the semantics of the operators, of the plus, minus?
No, it's on the wrapper. Then it's on the wrapper imports basically the acro algorithm. It comes in a couple of minutes.
Okay, and the thing on the right-hand side, it's just a kind of what, an assertion, or is it producing some code, or what?
Yeah, it produces some code about that, some basically forma or logic or formulas that we then will dispatch to Z3 to check that that's upheld. Yes. Okay. So it's basically logic, first order logic, what you are kind of writing, yes.
So you use this for static
analysis.
And saying that yes, your implementation is correct, or no, it's not? Or
well, it is being used to basically know when do I have to coordinate or not. Because if your operations commute, and then I don't need to have coordination, I go CRDT way, otherwise I will need to add logs. So the idea is like, okay, you still don't see the merge, but now you have to define the invariants about how your data type behaves with concurrency, and then you let the algorithm behind the scenes that indeed you don't see because it's hidden for you. Yeah. So actually, maybe I could have explained this with that slide, because the idea is to translate this into something that you could put in your distributed key value store and then have it replicated. And the idea is that the distributed specification, we throw it into some tool, a static analysis tool. First version was dynamic, too slow, not performant. So we throw it to this tool that basically checks that we can generate the ICRO basically to properly serialize the operations to ensure the convergence. But it's not only ensuring that the replicas will converge, because this invariance is telling you about concurrency semantics, right? So basically, you could put there other kinds of invariance, not only for conversions. So what does the Ordana did? That's probably one of the crucial parts of ICROS, is that it will derive information about what are the commutative methods and how does it do that. Basically, you have the information here, right? So you oh, you see, sorry. So you had the information about what were the effects of the operation with the postconditions and what is the basically semantics that you want in phase of concurrency. So then what Ordana will do is to give you information about commutative methods. That was also like something that, for example, Carla had been done. Also about conflicting methods, which ones not commute. And then it will find conflict-free solutions for the conflicts. And if not, if it couldn't find a solution for those conflicts by reordering the operations, then is when we lose logs. That was the idea. So you get this hybrid. So what is going on when you have an ICRO, after you get this ALDU set, that's an ICRO. You basically have object state, and your state is represented by the sequential data type. But there is the replication algorithm. And the replication algorithm will use the information at runtime of the static tool. So what we'll do is, like when you issue operations, it will construct a graph of operations, but it will append, for example, the happens before to keep the causality of operations when it does not commute. And it will also add these conflicts edges with information that it knows these two operations conflict. So then it will traverse this graph to find a serialization in which you don't have the conflicts. There were also arbitration, because sometimes you could not resolve, then both replicas had to take the same. It's very important that it's deterministic, because otherwise it will not ensure convergence. So I see that the thing is not here, the reference, but it's, I think, a couple of slides before. So I will not go over the algorithm. You can see it in the paper, because my goal was like, yeah, now we are getting closer. Oh, there is some strange thing going on here. Sorry about that. I will fix it for the PDF. Because now we can check, is this general purpose to build like basically application-specific RDTs. So we could implement the well-known CRDTs, some of them. Some things where we did not have CRDTs because you require coordination, but you can still use a stack and a queue. And then for certain operations, there will be the logs being put behind the scenes as a result of the Ordana analysis. And we could also build application-specific. This one is like some well-known benchmarking distributed databases that we use to basically compare that thanks to the static analysis, we could have less latency in some of the operations, because we could reorder, and then we didn't need the logs. And other people needed to put more logs because they could not do this reordering. So what did I learn here? Well, it is possible to augment these sequential data types with a distributed specification. We can go general purpose, but sometimes it will not be fully working without synchronization. Sometimes it will have to use logs. The static analysis was key to derive these efficient RDTs. The first version we will try in all possible serializations at runtime. It was terribly slow. And then based on this information, you could then use it at runtime to basically do try to run the operations without coordination. But if I'm a language designer, I see that I have a domain specific in Scala, but still it's a separate specification. What I am doing there is writing first order logic formulas, right? And actually, if you look at the specification already in that one of the LWT, here you have it, one word, yeah. As a programmer, it's stating the effects of an operation, but he might already basically written the operation. It has just said, okay, just add it to the sequential set. But you still need to specify in first order logic the effects, because we needed to feed it to the static analysis tool. right? The invariant is important, but if you look at this, if you want to provide like, or ease the development, it will be better that this will not have to be written by the programmer, because we need this to make happy Z3 in a certain sense, your static analysis tool, right? So, wait, let me go back. No, no. I went far too fast. So, no, went far too fast. This was the problem I was talking. Also subtle errors, because if you make some errors in these formulas, especially the post-conditions, what will happen is that then the tool will not be able to derive that you could have a ordering of operations that did not require coordination, so then you may end up with having too many logs, or some runtime maybe anomaly. And then, of course, you have a specification that has to be run. So the DLS specification has to be maintained with the code. And that's where the idea came, okay, let's try to apply some language design. Could I have a high-level object-oriented programming language for the sequential data types, where I define the concurrent semantics, but it is within the same language? That's the idea. It's within the same language. I don't need to keep up with the two walls. And if you make it that it's fully compatible to SMT, then you could get these first-order logic specifications for free. But I still want to synthesize real data types that I can put in a key-value store in Scala, and that it works. Okay? And that's how basically we came to with Kevin, to the fx, what was language. So basically, fx is going to be a subset of Scala, and then you get pretty much inspired by it. Just that when you parse it to the ST, it will be used for two things. First, to analyze and to generate the SMT code that then will be fit to the analysis. So basically, the programmer will not have to write these post conditions, because this is, by doing an analysis here, it could be generated and then given to Ordana, because you really still need the information about the operations to have a efficient RDT. And the second one, it will basically go through a Scala plugin to a Scala program that then you will get the ICRO. So if we see now, it looks basically misleadingly Scala, because it is not full power Scala. Scala is very big, and not everything you can basically map it, or not everything we need it, you can map it to SMT, right? And behind the scenes, you know that there are these operations, the effects of this, they are being generated. So it looks like kind of a Scala, because it gives you as well like a set as a data type. It is based on functional, basically, kind of a functional way of operating with these data structures. And then you could annotate some class with replicated, and this annotation, basically what it will do is that it knows that this from here will have to generate an ICRO data type, and it expects that there are going to be invariants that have to be upheld. So if you want the add-win set, now you can add the invariant, in which an invariant for an operation that you have defined in the sequential data type, and then it check, in this case you do, this contains the element. So it's much more simplified, although in principle, behind the scenes it is the same. It's just trying to hide some of the complexities to the programmer, basically. So if you wanted the remove widths, well then you change the invariant, but you don't need, you can still use the same trait, the same for the sequential part. Okay, so then fx could like get them from them. So how do we, Kevin validated this by trying to write the same portfolio of ICROs. It should be possible, right? Then it means that your translations to the SMT are correct, and then he added even more application specific besides the rubies. To basically did a bit of, I don't have time to go over the details, but it checked basically how easy it was then with the specifications. Go ahead.
Could you go back to the previous slide?
Yeah. Oops.
Why do you say it is really simpler than what you had before? Because you still have to write new things?
Because now, what I want is a general purpose RDT. I want to say, when they are concurrent operations, from different replicas, what do I do? So I need to maintain the invariant. But I don't need, as a programmer, to say what are the effects of after you do an add operation, what will be the effects on your program in the specification? Because you see it here. You see it on the code, on the body of your add. The effect of doing an add means that your set grows with one element. You already did in your implementation of the data type. But in the previous version, I had to implement it on the data type, but I had to write the specification to say what was going on. I repeat the question, yeah. So the question of Manuel is that it's not understanding what is the invariant. It's just checking that the element that you pass, it is contained in the set. So it's an AW set, and an AW set, basically, it's extending the trait of a set, and a set is just a regular sequential data type. So if you do an add of an element, your invariant, in this case, because the AND should win over any other concurrent operations that are happening, should be that after all the concurrent operations with the add, which could be a remove, which is the ones that don't commute, the element should still be contained on the set. That's what it says. This I cannot remove it, because that's what makes that it says, how do you want your replicated data type to behave when you have concurrent updates? That I cannot remove. But everything about what is the effect of adding the element, which was before, I had to say, look, adding the element is putting it, and then I had to write it in first order logic. And I don't want that the programmer has to do that, right? So that's what it went away, because you have this language designed to then compile it to the first order logic. Yeah? Yes?
Why do we need the copy?
Well, yeah. So this is because it is expressed purely functional. So when you do an operation, it will give you a new data type with the effect. But in the first iteration, that was very inefficient. It was not done. It was done with mutation, and then we had the conjecture, maybe if it will be expressed as a pure functional, would give also better performance results. And that's why, and also because by then my PhD student got completely convinced that Scala is the best thing in the world. So, which I will say it is, because otherwise Mira maybe and other people here kill me. So that's why it is, this is expressed purely functionally. Yeah. Okay, good. So we reached the end of this deal pin. Because then Kevin got even more ambitious. That was then him going more ambitious, because I was, wow, this is really cool. And then he's like, yeah, but Elisa, look at this. If I would be able to have like completely, that the language completely can be mapped to SMT, then I could basically have not only cross, because here we were generating the thing that goes to Ordana, but I could have correct replicated data types out of the box for the masses. That's what he called it, right? And that's where, when he put a lot of time into basically trying to have the maximum subset of Scala that have like the feel of a Scala. You have maps, sets, vectors, the list, so that you could have operations on this, as it will give more this functional favor. But that then it will be fully compatible with SMT, and we added one novel proof construct that basically that could express application-specific correctness properties. At the beginning, it was only for RDTs. So the idea was like, oh, now I can, without having to have a super deep knowledge on verification, because there is people that have done the proofs in the verification world by going the Coq way or the ACTA way. But what's our point was, we want to give tools to the programmer, so it should be easier for the distributed programmer, even if it doesn't have a deep knowledge on verification. And then, yeah, I mean, with this proof, it's like, yeah, then you could basically get automatic proof verification behind the scenes by discharging obligations onto the SMT solver. And that's what he did. The thing is, like, we didn't know when he started, it's like, how many CRDTs are you going to be able to do it in that way without basically only with the logics that SMT supports. It was not really clear, and we were surprised that of the amount of things that we could prove. Actually, I now see that I don't have the portfolio, but there are like about 50 CRDTs that have automatically proof, so you don't need to go into the cock, blah, blah, blah. But just by have them, you take the specification of Shapiro et al., for example, you put it in very fixed, which is quite close to the specification, and then with encoding the proofs, they knew the proofs. The proofs are manual in the papers. We only encoded them there. You could get like a free verification. And this is where we are now. We are now into like exploring the possibilities of this iteratively workflow in which you design an RDT, you implement it in very fixed, you get basically you have a trait for checking the state convergence, for the state-based CRDTs, for operation-based CRDTs, for deltas, for operation-based CRDTs, many of the families. And if it says correct, then you can transpile it again to Scala and deploy it to the system. And to deploy to the system, you basically need to give serialization. Again, the distributed semantics a bit. So by adding the serialization on the data type that comes here, he could put it into an existing distributed key-value store in Scala. If not, then you get, basically, that means that Z3 is complaining and gives you a counterexample. But that's not meaningful for your high-level programmer that doesn't know anything about first-order logic, yes, but not the complex logics of SMT solving. So basically what it does is that it expresses the counterexample in terms of the very fixed language so that you can then modify your implementation and then you can go here. We are still working on basically improving this workflow. It has been now like we had a summer school in September and there were like super surprising 6 other students who used the very fixed to basically verify RDTs, but also for other kinds of proofs, because you could use it for something else. I will take your question. I finished the sentence. But I cannot say this because we are still have not tried all the power of the language. So for now, we can say what we have done with RDTs. Now your question.
Sure, and it might be related.
Yeah.
How difficult have you found it to interpret the counterexamples?
Oh. Yes, so he is asking how difficult, how difficult it is to interpret the counterexamples, correct?
I'm making an assumption here also that the programmer is the one who has to interpret the counterexample.
Yes.
That's not objective.
So before last year, only Kevin could. Because I was using it and for my classes, and I wanted to show the students what we were doing, and then I got this, and it's like, Kevin, I don't understand anything. You have to go through all this code and deep inside and the identifiers because it generated SMT code, right? So it was difficult. And then he added this that made my life much easier. But okay, there is basically an AST that it gets generated from the code, right? So, and he analyzes it to go to SMT. So basically he added support to go the other way around. But this is something that he did to please me, and because I thought it was essential as well to have users of the language. Which will bring me to the second part of the talk. So apparently, but the second one I will do it later. I know, I told you. So the thing is like, this is very nice, but we are still exploring this, and you cannot use it for any distributed application. That will be my dream, right? But there are limits on what you can do automatically proof. And there are a lot of people working on theories to be added to SMT. There is a lot of people working on verification, like a la Koch and so on, where then you require the expertise. They can prove more things, of course, but I want something that is usable for the distributed programmer. So this is not yet there. That's why, well, what do I need to do? There will be failures, and I will need to complement this, basically. It goes beyond giving a programming model. I will need to provide tool support. I didn't need to wait till very fixed to know that, because basically tooling was essential when I started in 2007 to teach ambient talk. So, okay, Hadal Miller in the IQ was explaining all these war stories about supporting millions of Scala users. Well, I didn't have millions, but I had a bunch of master students and bachelor students doing thesis, going to the courses, who were using the language. And yeah, for the researchers, for me, with a text editor, and then I had the REPL. You cannot see the picture because it's all on raw resolution, but here there was limited syntax highlighting. A terminal with the REPL. The terminal didn't scare me from my C live, but apparently it scares a lot to people. And then what you see here is that this basically MacBook Air is talking to this phone and basically sending the hello. You don't, sorry, the quality, it's an old picture. And yeah, the students were always saying that they found an error in ambient talk. And it was not true, it's just that we were not providing any tool support. And they could not also reason about all these distributed events and how it works. Of course I could do it, the interpreter was in my head, but not them, right? And the error messages were also not good. So even though, I mean, I was not developing the whole interpreter, but when you work in a project like this, you end up touching a bit everything. So I could help them, but without me, they were like always complaining. And then Android comes and you are teaching them with phones an extra level or source of problems, because with Android, well, if you have worked with it, there is a lot of, by then it goes at such a fast pace that every year they are a new release, the things that on that version doesn't work with that version. So it's like, let's give them our devices so that everything works nicely. Yeah, no, they come with their own mobile phone because they are super rich and they all have mobile phones by then already. So then you have to account for all the hardware issues. So I realized pretty early in 2007 when I started teaching, this is not the way how to basically give a super cool programming model that Ambient Talk had on those for those days to users. So I started working within my PhD, another of this procrastination, about tools that allows them to reason about these distributed events. And I focus on debugging. So we had this programming model that we see, and it's again, okay, you have an error, so your intuition should be put a debugger, put a tool, and see what's going on. So try to understand. So the first work on debugging was basically not only giving access to the actors or the event loops and pause, but to have domain-specific features for the event nature. So when you pause and you want to step, you want to pause and step at the level of asynchronous messages. What we usually do in the debugging is that we have very good, well, we have debugging, very good, maybe debugging support for the sequential part of the code. But now I have as well the event-driven things, right? All these kinds of events. So that was one thing. I want to pause and step at the level of messages. I want to put breakpoints, not in a source code line, but also for asynchronous messages. And it had to be epidemic because since we were in these mobile networks, I will start debugging one mobile phone, and at every mobile phone that will encounter and that will communicate, the debugging session will keep infecting the mobile phones that you were debugging. So it was a dynamic debugging session. It was not like, oh, I have a whole view of the distributed system. It will just do this epidemic. I also had something to browse the history of messages, but yeah, it's like no time. You need to write papers, so it was in a hidden button command line. Again, command line is not so bad, but yeah, they don't like it. So just super fast, we start looking into what are the breakpoints that make sense, and you do this by analyzing your event loop model, and then like check like, oh, you can put it at sending or receiver side, and we started investigating what was. So, for example, one of the breakpoints I had in my debugger was that you could put a breakpoint on an asynchronous message, but actually you don't break the receiver, so in this case, the object shopping session that does the go, but I want to break when I get the result of the message. So even though you see the dot on an asynchronous message, who poses is the client code when you receive the answer. Once you were paused, you could also go then, it's like, have a stepping, again, at the level of messages. So if you are paused here in this kind of, this was the shopping. So when you want to buy, you need to know that you have the part in stock. You need to check the credit and that you can deliver. So if I pause here, when I ship these 3 messages, I could step into and the 3 receivers will pause. And that I could investigate, because the whole idea was like sometimes there were message interleavings between the actors because they were distributed, and I didn't know how that I end up into that state. So that was a way how to add online debugging, but at the level of the messages. And then it's like, how do I validate this? Well, yeah, let's do a user study. User studies are very hard, and this one is the first one I did. By now I have more experience, and I would do it differently. Of course, you will always try to do it differently. But we took the debugger to see if those features for the events were useful. And we did it with 22 participants who have done a master thesis or were doing a master thesis or had already had the course of ambient talk, because we needed that they will understand the ideas of ambient-oriented programming to then see if the tool will be valuable when you are a distributed programmer in that programming model. So what did I learn here? Well, they did value, because of course if you did not have a debugger that helped you to reason about all this, and now you had it, at least they value the tool. And you see this because this is the pretext before the experiment. This is the answers on the post-test. We have more positive answers on the post-test. And something that I particularly was pleasant to see is that the remedy debugger supported what they would expected that a debugger for a distributed programming language had to. So that was good, but they did not like it. The GUI was quick and hacked by me in Eclipse plugin. Neither the visualizations were up to date. The visualizations were still using the classical things that we use for sequential code, where you have lists of actors. This might not be the best way how to represent it. And basically it was pretty much list-based as how you would have it for a debugger in Visual Studio Code or for sequential code. So here, we need to work more on this. And this brought me like then, it's like, okay, I did for distribution. But a bunch of questions come to me, like, how do I deal with the non-determinism? Because I couldn't deal with timing errors, right? I mean, if there was like errors that only happen because of certain timing conditions, was very difficult in an online way, how I had. How do I apply it to different ways? So, wait a second. The non-determinism also, it's important because of the non-reproducibility, right? If you put the debugger again, with the timing things, it might be that we will not get at the state that the bug will reproduce. That's hard. Then, to the different concurrency models is because basically it was like, okay, it has to be that you should be able to use the domain-specific things for distribution. Even if you are not using actors, you could still be using communication sequential processes, or you could be using other models like threads, but you should still, could we make it general, what I had learned? The visualizations, I had some students working on it because, again, we are not there yet. Another of the questions, like, could we build a debugger which will be proof effect free? So you know that, well, this is related to this effect with the haze and bugs, that just by the fact that you have an online debugger attached to an application, it could be that some scheduling of messages does not happen because the debugger affects the behavior, and then basically you could not reproduce. So could we make a debugger that did not have this, adding these extra proof effect things? How do we deal with big amounts of data, especially in distributed systems? And then again, remaining close to the hardware, can I put this in memory and network constraints? Okay, so I will do one deal thing, but this one is shorter, don't worry, I will finish on time. So let me drink again and do the last delving. I don't know if there is any other thing in the meantime. Okay, so we go from PL to tool support. And I'm going to talk a bit about the work with my PhD student. By now has a PhD, is earning big money in Nokia Bell Labs, which is about Hydra and SPA, and it's how to make online debugging practical for the big amounts of data, distributed systems that handle a big amounts of data. So that will be big data processing applications. Because what you see there is that, okay, you have long-running computation, so there is a huge, of course, volume of data. And it is distributed in the sense that they are always remotely executed on a cluster. And that also could slows down the debugging cycle if you have to connect there. And so there are many programming models, so we are not studying what is the best programming model here, whether with events, with data. That was not the thing. The thing is like when I get errors, how do I debug these applications? And the thing is like if when we started in 2016, there was this paper that said that 37 of the reported errors were related to developer. So if you look a bit, basically you had things like code defects, so explicit errors inserted by developers, operation mistakes, like for example, file renaming. This was more like dealing with the underlying, for example, distributed file share system, and also a lot of misuse, like configuration errors, because there is a big technologically different software stack, and sometimes it's very easy to misconfigure something. So by then there were some debuggers, and well, there was a lot of logs. They take the logs, and then you had visualization on the logs, and then try to see what went wrong. But from the logs, you get very few contextual information sometimes, and they could not, took a long time to get what was the real reason from that the application failed. Second thing is like you had replay debuggers. So they will record. They were expensive, but they could record and then replay from the beginning. But since it's a long-lasting application, distributed system, you may have to wait like 8 hours of the replay until you could then start understanding, well, reproducing the back. And then if you did not get it by the first run, you need to go again to replay from the beginning. So it was costly. But there was this paper, Big Debug, that was actually trying to improve this, and they will only replay from the last checkpoint. And then, then I thought, this is interesting, but I want it a la Smalltalk. So those who are here that know Smalltalk, it has like this live debugging field. Maybe there is nobody, they are all in the live program workshop. So basically, it's like, could we build a debugger that is online? So basically, you debug the system when the bug happens, because my goal is to basically avoid the replays. But it will have some, of course, domain-specific features for debugging. So like, it will give you a centralized view on what's going on with the different processes, all at the same time doing things on data. Hopefully, it doesn't interfere with the execution. And the interesting part is like then you can do as well updates of the running system, so you don't need to stop and then start everything, but that you could deploy code fixes to the individual workers where basically the error happened. So live code updating. And that's how we came to out-of-place debugging. So in Smalltalk, we said that that's an in-place debugger. It's always there in your system, but actually I want the capabilities of my Smalltalk debugger, but in another machine. Because I want to debug in the developer machine what is going on the workers without having to go remote debugging as how you usually will do, right? So what it happened is that when there was an exception in the worker, it will wrap up a debugging session, it will send it to the master, and the master will serialize this and send it to the developer. And if you had another worker with exception, the master will be the one of coordinator. That's nice. You have infrastructure. It's a bit of like easier model than ambient talk because you can rely that the master as a point of communication with all the workers that are doing these functions with big amounts of data. And what's going on in the developer machine? Well, it is meant to be like in a small talk way. So a debugging session was nothing else than capture the execution state at a particular moment where the exception happened, and then reproducing it in the developer machine. And then there were a lot of other things, like for example, okay, remove the framework frames so that you serialize less data, because we are talking that these processes manipulate a lot of data. If you see that the exception happens 3,000 times in the same worker, don't send 3,000 times sessions and the developer will be overwhelmed. But basically make a composite debugging session, one exception, and then sees in all the records that fail. And then there were two strategies, because yeah, you are talking that you move the computation, but all your data where you are doing the processing is still in the server. So there we had here like taking the assumption is that when you will have errors many times, it was in the same partition. So you could move only the partition inducing the error. Okay, once you have this debugging session, it works as small talk, so you can be doing, in the IDE will record your changes. So you are debugging there, you can restart it if you need it. And then the code changes will be class modification, additions, refactories. It will be recorded there. And then it will compose a patch that you send to the master. And the master, it's good because, again, it has tools to know what is the appropriate time that you can interrupt these workers and push the batch to the workers. Now, as I said, there are many different programming models there. We only explored that idea with two. The first was for map reduce. Well, so this is like IDRA working on as an extension to Faro. And then basically you will get the composite exception. It had happened 3 times, so 3 workers had this exception that it said a reading number failed. And in this case, then you could have different strategies. Either you say debug all the failed ones, only the selected, or create me a virtual partition that looks like the one that is there when the error failed. We then also explore it in Spark. And in Spark, if you know a little bit about it, it works with replicated data structures. So then you also need dedicated stepping because you want to go to the next element that it's been added on that collection. So the next transformation that you do on an RDT or the next action. So it had dedicated domain-specific things targeted, in this case, for big data processing. And then it's like, this is very interesting. Are there other distributed systems that could benefit from a kind of a similar debugging so that we can reduce this latency of going and debugging always remotely so that we could do it locally to reduce the latency and to improve like the debugging experience? That's where we came to trying to apply these ideas, but for Internet of Things. They are not processing big amounts of data, but they are also event-driven. They also are deployed, basically, and if you need to debug, it's remotely. Here it was a lot of log-based debugging as well. And many times, well, when we started, many times it will be only a remote debugger that you could connect serially. By now it's also wirelessly. And then we pair with the group of Christophe, which were building a virtual machine for embedded devices to build these Internet of Things applications on WebAssembly. So the idea was like, we have the programming model is there. We will basically just use like C, or you can use Rust. You write your application. You use the WebAssembly VM to have your code on the device. And could we improve the debugging of these systems by bringing out of place debugging? So actually the architecture looks similar, but now we don't have a cluster with masters and workers, but we have an embedded device. So in our case, most of the times we work with the M5 stick hardware, where it has the Arduino VM. And then basically it will have this debugger proxy. From the developer machine, what you would have is like the Visual Studio Code, where you have your source code. It will then go to WASM, and it will have the views. So basically what you see as well in the out-of-place debugger. But interestingly, there will be a VM locally, basically running the application with some monitoring. So the idea is that the first, initially, is like, no, I forgot there is one animation missing. So if you have here the code running on your microcontroller and you get an exception, a debugging session could be asked that will be brought into the front end, and it communicates with a virtual machine that is at the same status than it is there. So then you can debug locally while you have your remote device over there. So here it's a bit, requires not a direct applicability, because if you look at the source code of a NeoT application, you have basically location code that it's location independent, so it's doing some computation. But there are sometimes code that it's about non-transferable resources. We saw this a bit with the clouds, because the non-transferable resources were the data partitions. I couldn't take all the data from the cluster to my developer device. But here, basically, they were a different kind, because we were talking about sensor data, about buttons, about networking messages coming there. So then what we were doing with out-of-place debugging doesn't work entirely, or only in some circumstances, because what we did with Matteo is that you will always pool these devices, these resources, right? So you bring the partition to you. So if you have like an out-of-place debugger here, it means that when you hit something like read or switch on the left, or read the temperature sensor, you had to go to the device and say, hey, give me the reading of this device and bring it there. But in these cases, there are a lot of these resources that work in an event-driven way, right? I mean, if there is like a MQTT packet arriving here from somebody else that is talking to the device, this is not something that you can reproduce while you are debugging online and you go to the next line. The callback will never be called here because it arrives there. So that's where, with the students of Christophe, we thought we extended it, and they already had an event queue in the VM, and we exposed it to the debugging side. So basically, when there are events like networking, or some, if you push the button, what happens is that this proxy will bring it to the local developer machine, and then you could debug it. So basically what you are having is a kind of simulation environment, but it's not really simulated. It is real because it gets all the events from the device. The device is not doing computation because it is here in the debugging, but all the events that happen for real on the microcontroller gets forwarded and offered to the developer. We are still working on this, and actually some advertisement for him. You can learn more about debugging for his talk on tomorrow. And now I really reached the end, because I see that you are all getting tired and want to have some coffee, so don't worry. Because, well, I hope if there are 3 things that you remember from today, because I know that sometimes the Delft teams might be losing people, is that distributed systems are very successful, widespread. So it's not something that was something very niche, or like when, like 20 years ago, it was a bit much more different than now. But they are still challenging to design and implement. So we are still working about, in the PL aspects, on how to ease the development. Because you cannot abstract the partial failures that will never work. You cannot abstract the fact that there is no global clock that is shared. You cannot abstract the fact that they run at different speeds. So the characteristics of distributed systems makes that it is challenging. And my personal take is that it is essential to explore the programming abstractions together with the tools. Basically, so that we give a full set of toolbooks to the distributed programmer. I just try to highlight you some of the work in this area, that I did with myself or with my students. And actually, if you are interested in these topics, I'm working with collaborators for making happen the second version of the future of the buoyant techniques, hopefully next year in ECUP, as well as making the second version of the summer school on distributed and replicated environments, somewhere else, not the BUV. So that's it for me. I need to thank, of course, past current members of the group, as well as the main collaborators that I have since I lead the group. So this is a picture of us having some lunch and fun. Thank you. Yes, sure.
Do you have any questions? We need to have a question for the drinking pause. All right, just to start, I have a lot of questions, but you mentioned repeatedly a couple of times, probably like this, the challenges of working with the real constraints on memory and work when you are deploying in a distributed system. So could you elaborate, because it seemed like it's still an open problem on all of these stages of development. So where do we stand on there, and what can we do?
Okay, so I don't do research in the implementation techniques to make it faster. So I just can tell you about my experience as programming those systems. And many of the techniques that we develop sometimes are for, they are, let's say, the performance comes later. First, we develop the programming model, and depending on the target application, then the performance will come later. So it's the same in ambient talk. We were the same. And then when you go and you try to have it that it could be more than an academic, so that you can show the potential of the technology and you use the devices, here is where you encounter that maybe it doesn't scale your technique. So I'm not saying that everybody now has to go and start looking at scalability only, because we also need to have pure research about how to use the programming, but it is true that we still, there are techniques that we still cannot scale as how we would like. Even if you take, for example, the idea of the CRDTs is very, very interesting. But many times you have like assumptions of like fixed number of replicas that makes that the amount of data that you send over is restricted. And it is also interesting to keep always the line coming from the mobile networks, because there you don't have infrastructure, and then you go to a smaller devices, and it's like, okay, would my CRDT still work if I have a dynamic network? And it's working on not super low level, because we always try that we have a minimum VM. If you see, I mean, there are many people that work on Internet of Things systems that they go very low level, very constrained devices. We are not at this range, but an SP32 kind, but it is inside of the M5 stick, still is much more reduced than this computer or a cloud server. I mean, big magnitudes. That's also, and I think also because I have kept this interest as well, probably. My nerdy bit of doing these things with devices. And second, let's not lie, because I need to get funding. And if you look at industry, many of the people will not be on the most constrained, but they will be on the middle range, not full-fledged like this, but a cheap device, microcontroller, that they can afford to put into their production, and that they basically allows them to package it as an Internet of Things kind of thing. So now, that's why if you look here as well, we have people like Stefan or Tom's group. I work with the VM people as well, because you need to work with them. Maybe there is another tandem. I want to have my super reflective language, whatever, but I also need to work with the people of VMs so that this is scalable. Does this answer your question? I went, I think, like, woo, woo. I went all over the place.
Yeah, that does answer the question. Thank you. Do we have other questions? You can, in fact, ask questions. This is a workshop, right?
They did ask some questions on their defense.
Yes. All right. At the last slide somewhere, you don't need to go there. This is a wonderful picture. But you mentioned that we need to explore novel programming constructs and abstractions and whatnot. So, so far, your entire story was, and then I had this idea, and then it worked wonderfully, and it did wonders, and then I had another idea, and it was also wonderful. So did you have some,
Really?
yes.
Did I found somebody who had a wonderful idea.
Sure.
I tried to implement it, and I found a bunch of problems to work on.
There were a lot of faces there. Sure. I'm not saying you claimed all the fame to yourself, but I do say that this all looked like a series of successes. So can you name maybe one idea that was really like, okay, this is a very attractive novel concept that probably will totally work, and then it absolutely didn't?
Yeah, sure. I mean, of course, you want to show the success, but to reach there are a lot of attempts that fail. The C-cross algorithm had this idea of making a general purpose, starting with Bayou, all this. But yeah, we were serializing all the operations at runtime, as I said, and it was terribly slow because the more operations you get, you had a ever-growing graph of operations that you had to topologically sort. So it will never work out. Although how they look like, it was an extension to JavaScript. It looked more like the effects. So for the programmer, it looked nice, JavaScript objects, like a la JSON CRDTs of Clement. But then with this little invariant, it looked nice, but it was not performant. The E-cross, they are performant, but in my opinion, it looks ugly. Because you have this specification. So then you get into the success, if you want to call it, because you combine the best of the two worlds. That's one of the things. Other things that fail terribly. The out-of-place debugging, so keeping in this. We were trying to do it for production systems, and that was like really production systems, but not a la cloud. And that was not giving us like to have something where these features could really help. So we had to retarget. In a certain sense, it's like, okay, do we throw the idea, or is this something where it could be interesting, this kind of small talk-like debugging, but externally? And that's where we came to the data processing. But failures, there are a lot. So if maybe you were not paying attention to the dates, but I said that I started in 2005, but the paper, I mean, Ambient Talk is 2007, so it was like 3 attempts to get funding for a non-Flemish speaker to stay in Brussels. So I spent a lot of time trying to secure my funding. So in these times, I did all leasing work in Ambient Talk 1, which was thrown away because then we did Ambient Talk 2. So there are a lot of things that I have left in the drawer, or that they are not properly published, like exploring interrogative debugging for actors. It is a workshop paper, but if you don't have a user study, they don't want to publish it on anything serious like ICSI or whatever. So they are. But that's not what people like to listen sometimes. So by all means, my idea was not to say, oh, success after success, was more like to try maybe as well to inspire that sometimes you might have an idea. There is somebody who seems to solve your problem, and then you try to implementing, and then sometimes you will need to adapt it basically, and then you have a success. Sometimes you really need to work really hard because this super cool idea, it's very nice, but it does not work in practice. I don't know. That's my take.
Yeah.
So
Thank you
don't
very much.
Persist, please. If I would have stopped the first year, I wouldn't be here today.
Exactly. So the learning happens at the failures, and the successes are just monetized on that. All right, last chance to ask questions. In that case, I close the session, and then we go to the coffee.
Yeah.
Thank you very much.
Thank you all.
Thank you.
say a word or two?
Thank you. So welcome everyone to the first technical session of Rebel. And Kento is going to talk about periodic and aperiodic task for FRP.
Thank you for introduction. I'm Kento Sogo from Tokyo Tech in Japan. Today, I will talk about periodic and aperiodic task description mechanisms in an FRP language for small-scale embedded systems. The objective of our research is to enable concise description and efficient execution of timed behaviors in an FRP language for small-scale embedded systems. To achieve it, we propose an extension of MFRP and FRP language. We introduce mechanisms for describing periodic and aperiodic tasks to MFRP. The mechanisms include types for time-varying values that express their update timings and runtime system that executes periodic and aperiodic tasks efficiently. As a contribution, we can reduce power consumption and execution time by the runtime system. Here is the presentation outline. I would like to begin by discussing the background and motivation. First, I will explain MFRP, an FRP language developed in our research group. MFRP is an FRP language for small-scale embedded systems. The program on the left is a simple fan controller system written in MFRP. This system measures temperature and humidity, calculates discomfort index, and determines the state of the fan from it. An MFRP program consists of definitions of time-varying values. Time-varying values are called nodes in MFRP. An MFRP program can be represented as a directed acyclic graph with time-varying values as nodes and their dependencies as edges, like the figure on the right. Program execution can be viewed as continuously updating time-varying values along their dependencies. The execution cycle is called iteration. Now, I'd like to talk about the motivation. Let's consider this system, a fan controller with two temperature sensors. Temperature sensors are located on the room's floor and ceiling. When the temperature difference exceeds 5, the fan is on. The fan is written like this in MFRP. When the temperature difference is close to 5 degrees, even a slight temperature change can cause the fan to turn on or off, resulting in unstable fan operation. Therefore, some modification or improvement is necessary. Consider changing the code so that the fan is updated every 1000 milliseconds. This code seems good, but it has problems. We assume that iteration interval is dependent of time. If iteration interval is larger than 1 millisecond, clock ms may not increase by 1, and the exact time to update fan may be overlooked. Consequently, fan is not periodically updated. If iteration interval is smaller than 1 millisecond, the condition may become true many times in 1 millisecond, which would cause the fan to be updated too frequently. It is possible to describe it more precisely like this. Node fan timing represents the next update timing. When clock ms is greater than or equal to fan timing, fan is updated. However, this is a little complex. Moreover, even with the more precise description, reading from the temperature sensor is performed more frequently than update of fan. And then, power consumption increases. In summary, the efficient execution and concise description in MFRP are issues. I will now introduce a proposal to address these issues. We propose EVMFRP, an extension of MFRP. Language mechanisms to express periodic and aperiodic tasks include types for nodes that express their update timing, and operators regarding update timings such as merge, partialization, at now. Besides, EVMFRP provides runtime system to execute them efficiently. The concept of nodes in EVMFRP is different from the one in MFRP. The MFRP runtime keeps updating nodes repeatedly. So, nodes in MFRP are viewed as continuously time-varying values. On the other hand, nodes in EVMFRP are basically discrete. In EVMFRP, discrete nodes are updated periodically and aperiodically, and continuous nodes are obtained from snapshots of discrete nodes. Discrete nodes have their update timings as types. Timings of nodes are specified by timing annotation. For example, this code shows the declaration of I/O nodes. The variables TMP and HMD respectively represent temperature and humidity. Node node temperature has a periodic timing 500, 1000. This implies that node temperature is updated 500 milliseconds after program start and subsequently every 1000 milliseconds thereafter. Node humidity has the same timing of temperature, and the timing of node fan is inferred by the EVMFRP processor. The motivative example discussed previously is described like this in EVMFRP. This code is more concise and precise description than that in MFRP. Next, let me explain features of EVMFRP. V at last n gives the value of a node V on n updates before. If at last n is applied to V, V must be defined with at least n initial values. This shows that temperature history has last 4 measured values of temperature, and a moving average is calculated using temperature history and at last. It's the same for humidity. Next, partialization is an operator that converts the timings of a node into a partial timing. Partial means, as shown in this figure, the original node always occurs at the same time when the partialized node occurs. This is an example program written in EVMFRP. Fan controller, this system measures temperature and humidity every 1000 milliseconds and calculates moving averages of them using at last. The frequency of calculating discomfort index is reduced to 2500, 3000 by the partialization operators. As node fan is dependent on node Ti and node Th, node Th is dependent on node fan. The EVMFRP processor infers their respective timings to be 2500, 300. Let me explain a little more about operators. The merge operator generates a new time varying values from values with different timings. This operator requires 2 expressions and a function. As shown in this figure, when one of the expressions occurs and the other does not, the result is the one that occurs. When both expressions occur, it returns f E1, E2. Next, V at now generates a continuous value from node V. V must have an initial value. While a discrete node cannot be referred to by a node with a different timing, continuous value can be referred to by any node. So at now is useful for handling nodes with different timings. A typical use case of the merge operator and at now is synchronization. By using the merge and at now in combination like this code, value with different timings can be synchronized. Discrete nodes can have aperiodic timings as well as periodic timings. The timing annotation of an aperiodic timing is represented as this. A node with an aperiodic timing is updated when the hardware interrupt corresponding to its level occurs. In this code, node PIR is defined with aperiodic timing PIR, and PIR will be updated when an interrupt of PIR sensor occurs. This is an example program using the merge operator at now and the aperiodic timing. This is a system with an LED and PIR sensor that uses infrared light to detect human. In this system, the LED turns on for at least 10 seconds after the sensor detects a person. Node LED is defined in this way. When node PIR time occurs, LED becomes true. After that, when timer time occurs and the timer time minus PIR time is not less than 10,000, LED becomes false. Here, let me explain semantics of EVM-FRP. Sequence is types for distinguishing the temporal properties of nodes. Each node is statically assigned one of the 4 sequences. This denotes, first one denotes a discrete node with timing theta and L initial values. Second one denotes a continuous nodes which can be obtained by at now. Third one denotes a constant node, which is a node defined as a constant value. Final one is not assigned to a node intentionally. It is an error in type checking of sequence. We define the type system for sequences. The type judgment guarantees that nodes are updated at specific timings under the assumption that worst-case execution time is sufficiently small. WCET-aware compilation is a future issue. Let's move on to the implementation. We implemented a prototype compiler of EVM-FRP. It generates 3 files, a C++ source file of runtime code, a C++ IO code skeleton file, and a header. The IO code skeleton is the platform-dependent part of a program. The developer needs to fill it in. It consists of 3 kinds of functions: input function, output function, and initialization function. For example, an input function includes sensor measurement, and an output function includes output to GPIO. Initialization functions include device initialization, timer setting, and interrupt configuration. Next topic is memory management. A discrete node is managed by a ring buffer to enable retrieval of its previous value. It is compiled into an array with the number of initial value plus one element. A continuous node is compiled into a function as it is generated from a snapshot of a discrete node. A constant node is compiled into a constant variable. The runtime memory size is bounded. This is because, like MFRP, even MFRP prohibits recursion. Next, let me explain how periodic tasks are handled in runtime. The time to process all periodic node updates in a program is controlled by one periodic timer interrupt. The occurrences of the timer interrupt must cover the occurrences of all periodic nodes. If a program consists of nodes with two timings, 500, 1500, and 1000, 2000, the timings of the timer interrupt is 500, 500. The runtime counts the number of times timer interrupt occur and decides which nodes should be updated. In this example, a node with 500, 1500 is updated on first, fourth, seventh interrupts. On the other hand, the time to process nodes with a periodic timing is controlled by a corresponding interrupt. The compiler generates a function to update nodes at each aperiodic timing because we assume that an aperiodic event does not occur at the same time as other periodic or aperiodic events. This figure shows how to control periodic and aperiodic tasks. When an interrupt occurs, the interrupt subroutine sends its ID as a message to the event queue. We use free RTOS queue for the event queues. In the free RTOS task called the main task, a message is dequeued and identified which interrupt has occurred. And then the appropriate update function is called. This is how runtime works. Next, let's move on to the evaluation. We performed an evaluation of MFRP and EVMFRP for comparison. We measured program size, execution time, and power consumption. The program used in this evaluation is fan controller system. We used two boards, Arduino Uno compatible board and STM32 board. First, we measure the size of executable files compiled into for Arduino board. The result is depicted in this table. The text section is larger in EVMFRP because the runtime of EVMFRP depends on FreeRTOS library. On the other hand, the data and BSS section is larger in MFRP. We believe that the reason is because the MFRP compiler allocates runtime data except for primitive values in the static area. Next, we measure the execution time without I/O processing. We recorded the execution time for each iteration in MFRP and each update function processing per timer interrupt in EVMFRP. The difference between min and max is larger in EVMFRP. This figure explains the reason. Node DI is updated less frequently than temperature average. EVMFRP has advantage of eliminating unnecessary calculations. Finally, we measure the current consumption during execution. In STM32 nuclear board, we use wait for interrupt instruction. These figures depict the result. The EVMFRP runtime performs intermittently and saves power. Thus, the advantage of proposed method is that it can reduce power consumption in the interrupt standby state by using instructions such as WFI. That's it for our proposal. Next, I would like to discuss the related work. Here are some related work. Event-driven FRP is an FRP language well suited for interrupt-driven microcontrollers. Continuous time-varying values behaviors change only when a discrete event occurs in EFRP. This semantic is similar to that of EVMFRP. Priority-based FRP is a reactive programming model. It originates from the FRP language that introduced priority to EFRP. The method of task scheduling is based on the abort and restart model, in which interrupted tasks discards its previous execution state and restarts from beginning. Synchronous languages such as STL, Rooster, and Signal have been used to implement embedded and interactive systems. Some synchronous languages explicitly handle clock. In our work, the clock equivalent is introduced using types for nodes. Lastly, we would like to discuss the conclusion and future work. In conclusion, we propose mechanisms for describing periodic and aperiodic tasks and designed and implemented EVMFRP, an FRP language with the mechanisms. Besides, we performed evaluation experiments that shows that the proposed mechanisms realize efficient execution of periodic tasks on resource-constrained environment. Here is future work. First, as use of the operators, such as merge operator, can be confusing, language design needs improvement. Next, we performed evaluation using a simple program that only employs periodic nodes. Thus, we need to evaluate based on practical scale application, including aperiodic tasks. Finally, real-time aware runtime design is also a future task. This is all for my presentation. Thank you.
Is there some question?
So I noticed you had some, oh, sorry. I noticed early that you had some kind of iteration. There we are. I noticed early in your slides that you had some kind of iteration. Is there a bound on that? Or did I misunderstand what I was looking at? I saw, so it was a directed cyclic graph as opposed to a directed acyclic graph. And I thought that you were suggesting that that suggested some kind of iteration, perhaps finding a fixed point. If not, then that answers my question as to how you can be real-time reliably. So, yeah, never mind. Sorry.
Sorry, I'm not. So, excuse me, can I hear your question again?
I can try. Maybe slide 3 or so.
Is your question related, generally speaking, to data flow programming language?
Yes, there we are. So, did I guess correctly? No, it's 5. All right, so that iteration at the bottom, does that mean that there could be some interrelationship between the fan and the TH that would require iteration to cease or to, sure.
Sorry, I can answer. So, okay, in this case, our language, so the graph of time varying value should be DAG, so no directed acyclic fast. So, yeah, actually, so in this graph, so this is a, how to say, so dotted line. So this is a reference to the past value. So this does not affect. So okay, so I think how to say, the fan does only reference the current value of TH, but the TH had referred the previous value of fan. So this can be done in the without any. Okay.
A short one about your evaluation. Could you show us the slide? There is something that I have not understood. Next one, please. And again, the next one. Yeah, so I'm a little bit confused because for MFRP you say per iteration, and for EV MFRP you say per interrupt. So how do the two things compare?
Update function per timer interrupt is this includes counting the time of timer interrupts and identifying which node should be updated and updated nodes. So, and iteration is node updates. So
I don't understand your answer.
Yeah. So the execution mechanism of MFRP and the EV MFRP are a bit different. So we how to say, we just compare that one, okay, so in MFRP case, it's just one iteration. This means that how much time to update all the nodes in the program. So the in case of EVMFRP, so we use part-timer interrupt. That maybe correspond to. So can I have the previous slide? No, second graph net. This one. So yeah, this roughly correspond to the how to say execution time for how to say this time interrupt, and then do so, and update the function for the node with periodic timing. So this in case of our how to say our setting, so without using without using aperiodic event, so that roughly correspond to the program that's how to say the same. That's over the MFRP version. So that this requires update of nodes in that program. We just how to say we just measure the execution time of this function. So that's the answer for you.
I also have a question, a clarification. Can you have a periodic task triggered by internal events? Or is it always from the outside?
Yes. Interrupt configuration is written in C++. In IO code skeleton. So you can write it in IO code skeleton, and
But can you trigger a task, for example, when a Boolean goes from false to true?
Maybe it's possible. We have to, yes,
Yeah.
tested kinds of configuration.
Okay. Any other question? Thank you very much.
Thank you.
Oh, good.
You want
Excellent.
me to switch it already?
Sure. Oh, you see my desktop. That's not as helpful. Let's see if this works. Sort of. And then the mouse does not want to be. Is that your mouse?
No, it should be yours.
Oh, it's just interestingly slow. All right, I'll be patient. Not that patient. That. I think I'm in business. Might mess up one of my demos later. All right.
We have a few minutes if you want to try to fix that.
Sure.
In case some people are joining
That'd be nice.
online.
I think you can probably do it from here.
I think you're right.
You need to turn on the application of the screen.
Yep.
Rather than having two screens, one on the laptop and one on the overhead.
Okay, that's good enough. All right, now it's in the screen. Yes, it is mirroring that I want to do. Let's try. There's lots of uses of the word mirror.
You need to turn on mirroring in the display settings. So if you go to systems, system preferences, and display, it's over somewhere. Where the hell is display? There,
It's displays here.
yeah, there it is. And
I
somewhere.
think there it says hold option while dragging. If you
No, sorry, yes, display settings and mirror. Where the hell? They moved it.
yeah.
I know. I think you're right.
There
Let's
it was
say-
saying that if you hold option while dragging.
That was it. That was actually it. I'm
Yeah.
sorry. I just saw it. I'm sure that would also work.
Okay.
But use as
Perfect.
mirror.
Yes, yeah.
Mirror, yeah.
And then mirror. Yeah,
So we have the
nice.
same
Ah,
one
that
first,
works as well.
hopefully.
All right. I think that will be nice. There's some, I guess, a counterexample that does not fit on a slide.
So, yeah, thank you. Kevin is going to talk about thorium.
So I hope that some of you, some of the old timers, will remember me from back in the day. So SPLASH 2014 or so, I just finished a project monitoring metric temporal logic, and didn't quite know what to do with it. It was sort of fine, but you know, if you were monitoring something that was going over a network, something like that, it was easy to say, all right, I'll tie it to that. But I felt like it could be used for some, you know, just internal performance, or I guess requirements. And then I really had this problem of when relationships exist between multiple entities that don't know about each other, you can create a monitor, but then how do you make sure that you know when to kill it at the right time? And so then, yeah, there were all these presentations about this thing called Rescala and distributed Rescala, even better. And it sort of inspired me to think that, that there might be a way to have a declarative language that would, yeah, somehow make it possible to get these things in. I'll just give away the ending. I haven't gotten to that part yet. I had several detours along the way. At my work, so I work at Southwest Research Institute in addition to being a student at UTSA, a very slow PhD student. And you know, there we used Qt, and we had some very complicated applications that did need to be dynamic. In response to some event, they'd rewire the dependencies. But where that happened in the code was kind of up to when the person who was assigned to do the job thought they might like to do it. So, you know, they'd set up some kind of a listener and an event fires, and now you're in a different file from where the original flows were set up. And so I didn't care for that. And I think the same problem really does exist for the reactive extensions as well, even though they were quite popular. And it did come back, I think, 1 year later to try to propose and demonstrate how you could use metric temporal logic as an operator inside reactive extensions. But at the same time, it's not glitch-free. And that glitch freedom thing that was being touted for the Rescala and the distributed Rescala was pretty exciting to me. So, so I returned to it, but being where I work and whatnot, I decided not to go with Scala. So the opposite decision of our keynote presenter. And so there was this other implementation out there, Sodium FRP, and it ended up informing a lot of my decisions about how I would actually approach things. But the problem, as I saw it, was that, and I don't think there's any debate in this room, that people have a hard time reasoning about what reactive programming or programs are going to do. But in my experience, and maybe this room differs, but normal programmers maybe tend to prefer the non-glitch-free frameworks. They like the reactive extensions are really popular. As I said, it's easy to get started on the previous slide, but then yeah, you don't end up, I feel, in as sound of a space. So my goal is to provide a glitch-free reactive system for, and I worked really hard on this term. It said legacy at first, but imperative experienced programmers seems kinder. I went with a language instead of a framework. I taught a class trying to introduce these concepts, and the students were able to cheat by modifying mutable data structures and things like that. That the information was only supposed to flow certain ways, but if your language allows it, then you don't behave as well. So language instead of a framework, and I really wanted that dynamic feature because it's something, I guess, that was just in the spirit of how we worked at my work, that you would put together a simple system, and then if tasked to do some different job, you'd spin up the parts you need to do the job and tear them down at the end. And so I was really excited by the way the original FRP, the Fran from Conal Elliott, had a switch operator. But because, well, I was excited by it because it was a declarative way to describe changing it. The reality, though, I'll get to that in a few slides. The syntax, the user experience, I didn't think was as good. And so my goal is to put together something with a workflow like this, that you have a program in a language of its own, this Thorium language, and it will entail or contain some declarations, some bounds, although the bounds are specified on the command line, and then some number of properties that you wish to be true of the thing that you've described through these declarative declarations. The workflow is that it will negate the properties. It does this because if you can find a flow through the state space of the system that is the opposite of the property and is also something that declarations allow, then that gives you a counterexample. And so that then can be presented to the user. And although I did ask the question about how do we interpret counterexamples, it is at least better, I felt, than expecting programmers who might be able to specify their program to be expected to write proofs of the correctness of their program. So all right, the approach. I mentioned that there was this notion of a switch statement, and that the idea there was that any reactive value could have, you could have a reactive value made up of reactive values, and it would swap out the definition of that thing. And that is powerful enough, of course, to do a great deal. But I thought, all right, what if we instead bundle them up into something that's like an object, which programmers are more comfortable with. But within those objects, they have to be, everything has to be a declarative statement. It's limited to the reactive operators. But that if you want to do anything dynamic with it, you will do so by swapping out a reactor. And that has the interesting effect, which I discovered, I guess, at this phase in my development when I finally got this working, that you end up with a name for everything. So if you were to allow yourself to grow without bound, sure, if you're going to have an arbitrary length pipeline, at some point you would cease to be able to name the things because you've got a container. I don't yet support containers. Or you have a linked list of processing stages. And I have basically issued all of that for now. And so you end up, yes, with the ability to refer to everything. And at the top level, even though the internal structure might have changed a bit by swapping out one of the stages, fundamentally the top level flow continues to be the same thing. So part of it is to experiment with how well that limitation, I guess, supports real development. But then, well, we'll get to the end. But I am at a stage where it's not yet practical. So all right, the basic rules and this terminology comes from the sodium FRP. It's a little unusual for those more familiar with the traditional. But I like the word, at least cell, because it is an analog to a spreadsheet cell. It's a thing that holds a value, and if it's defined in terms of other cells, if those cells change, which is what I say next, then it will change automatically. The stream is a stream of events. I feel like that was a change you didn't necessarily have to make. Stephen Blackheath, the creator of Sodium FRP, I think event would have been all right, but it's an event stream. And the idea was that you'd, standing in a river or a stream and whatnot and things flowing by. All right, so something concrete. So this is my syntax proposed so far. You've got, a name for this object. The constructor parameters go at the top. Those are actually members but they're not declared here, other than to say that there will be some stream of, I use the data type unit to say that these are like button presses. I don't have a value, but you know, it doesn't say what they're going to come from. That is defined by whoever creates you. But inside, if you're going to declare that you have a thing, this is an accumulator, so the value, then you're going to have to define what the rules are for updating. And I'll describe all these operators in a little more detail, but this one boils down to increment the previous value by whatever this increment comes in. Every time it has, increment has a value. One of the distinctions between this and some of the early things you mentioned, luster and esterel and whatnot, is that there is that notion of the cells and the streams. And so the streams are allowed to just not have values, but cells are absolutely required to have a value at all times, which is why this cell needed to have an initial value. And then I have a couple of properties. And I believe the first one's true, but the second one is deliberately false, so that I can go later on and show you a counterexample trace. But all right, so the operators that I said it supports, there's lift and snapshot. That basically means you've got some function of base data types, ints, reals, it's all that's supported right now. And you describe, or basically define something in terms of maybe a combination of cells and streams, or all cells. If it's all cells, you get a cell. If it's a combination, you get a stream. And it will sample either, this is something that's not true of the sodium, but either the current value or the previous value of the cell that you want to work with. And you have to be careful, think more or less as the previous case, to create, or not to create cycles that are not supportable. So the next value, maybe I should say the current value of A cannot be 1 plus the current value of B, while the current value of B is 1 plus the current value of A. So you can write illegal things, but when I didn't allow that, it used to be that if an event came in, it had to sample the old value, which is taken from sodium's semantics. And you just end up working really hard to say really simple things. This is, I guess, my previous example, which I will return to. The accumulator actually looks really nice if you have no way of describing the difference between current and old value. But yeah, other things just didn't work as well. But as I say, it's all cells, they're cells. Hold is the mechanism for updating state. That's the thing that we saw with the, basically an initial state. That must be a cell as well, or a constant. And then dot dot is to describe, what will happen in the future of the lifetime of this thing that has been defined. So when those updates arrive, it will take on that value. If no updates ever arrive, it keeps the init value forever. There's a filter, which the left side of that has to be a stream containing events or not. And the right side may or may not be one. So effectively, there's an inherent snapshot of the value of that condition in case you just want to turn on or off a switch. And then merge. So one of the other things about the semantics here is that all of the events occur simultaneously. Maybe two external events came in. If you had two stream inputs, if they place values on them and then call your run, then I guess they could make them simultaneous. But even if they aren't, if you have functions of your input, then and those are event type, then they will be simultaneous. And there might, and there often is, some need to resolve priority or handle the case where two of them are active differently from the case where one of them is active. And this just allows you a way to do that.
So you say that all the inputs are always present?
No. Any stream input is optional at all, like any stream value is optional at all times. No, I was just saying that any event that is active within a transaction is treated as simultaneous. No ordering, regardless of the topological order of the expressions. And so this operator is just important, that there be some way of describing that merge. Then, the approach is that when you do not have subreactors, the case that works reasonably well, actually performance-wise, you create a single trace. So that trace contains all of the members. Basically, if it was a cell event or a stream, I shouldn't say that. If it was a cell event, it's very easy to say, you will now have a an aggregate data type in Z3 is the SMT solver we're using, it will have an int data type in there. If it is a stream, then it will be a stream int, which is basically just a maybe, if you use the Haskell term, so that the SMT solver can check for the presence or absence of the value. And every sub-expression, and this was a simplification for my sake, it may not have been a good one, is also expanded out so that, I think that's there, so that if you need to, you can look at the values of the sub-expressions within a trace, but if you've done something particularly foolish and obviously foolish, you won't need to see the internal state to understand why it has gone wrong. But then you will specify some number of steps and then a property, one of the potentially multiple properties you declared that will be checked in this run. The SMT solver, as I said, flips the, inverts the sense of the property. So if the property is that the value will not exceed 10, then it says the value will exceed 10. And then, more or less as it was in the diagram, if it can't be satisfied, great, you report to the user only that it will not be satisfied in k steps. And if it can be satisfied with the inverted property, that means that you found a counterexample. And so, yeah, I do want to say this. This entire approach, this way of doing a bounded model checking, the advantage is that even properties that might have been, say, undecidable in general, things tend to be decidable on any finite set of steps. And so we can basically just feed it into the SMT solver and it will give you these answers even if you couldn't write the proof. And so that is what I'm targeting. But a trade-off that I've made is that because it's finding a counterexample in a finite number of steps, that's the definition of a safety property. And there are lots of important safety properties, but there's also liveness, the idea that, the classic one with an elevator, if you push the elevator button, eventually the elevator will come. And honestly, you're not usually satisfied with that answer either when you're dealing with LTL because it really doesn't say much about when eventually might come. But we will say nothing. Once we reach the end, any unsatisfied, let's call it obligation, is assumed to become true. So that's necessary for handling things like globally. So globally means at time 0, if you say globally this is true, at time 0 it must be true and every time afterward. Well, one way of defining that is to say that globally 0 is true if it's true at 0, and if globally true is true at time 1, and so on and so forth for time 1. Eventually, you reach the end of the limited number of steps, and you have to say something, and the something we said was what's called the optimistic semantics, and that really eliminates the utility of liveness properties at all. Everything ends up being satisfied. But all right, so back to this example, we can understand it perhaps, depending on how quickly I went through it. But perhaps a little better, we can understand that it's going to start off with that value at 0, and then when the increment button press, if you will, valueless input arrives, it's going to kick off that at, and I did forget to mention the syntax for that, sorry. That's another version of a snapshot, but a snapshot where you are not doing any math on it. So 1 at the event of an a unit or a valueless thing occurring, creates this stream of integers, which are the increments, and then, basically whenever the increment comes in, the value is going to go up, and so it should be clear that that claim I made at the bottom, that globally, meaning for all time, the value will be greater than or equal to 0, that part's true, and less than or equal to 3, and that's not true, assuming we test it with more than 3 steps. So I did. And I end up with this as the output. It currently does actually output optionally LaTeX, so it actually does look like that, assuming you look at it through a LaTeX viewer. And what it is telling you is that, and honestly it overachieved a little bit, but it basically just said if the thing is just constantly on, we exceed our limit. But this is where I got to that question. I was like, how do you interpret it? Because I don't currently highlight the point at which the property is not true. And in this case, it feels like it would be really obvious how to do it. And in other cases, it's not as obvious. LTL expressions often capture what you mean, but they don't necessarily do it in the most straightforward way. And so I do not yet have a good answer for how to maybe point a person in the direction to say that, yeah, your problem is that, that you kept incrementing too often. And basically, it went bad at this point. So we can see that, sure, it went bad here because we know what we're looking for. But the statement I actually made was that it will globally be between these two values. And that was false at time 0. And so the property is actually false throughout, even though the sub-property that made it false became false later on. And so, yeah, it's an unsolved problem for me, how best to fix that. And there's something I cannot possibly fit onto a slide, which is every sub-expression spelled out, showing how it got into the state that it got into. Even in this case, it grows bigger than what can be shown on a slide. But all right, so sub-reactors. Same basic operation. And to the extent possible, all of the processing and the logic is the same, with one change, that any expression that can produce a reactor is treated quite differently. If the reactor took a stream as its input, I'm not going to, as I would for my snapshot operation or my lift operation, take its current value. Instead, I'm going to allow that stream to be captured and used as the input, the continuously changing input to the reactor. But the other thing that I do is that in the model, that's next, I do not store this entire reactor. So if a reactor can be created at time 0 or time 1, then I will create a new numbered reactor as part of the model building process, put it into an array, and then put the number in the slot. And so that number ends up acting as a pointer so that you can then swap them out during the rest of the processing using the same hold logic that you would have used otherwise. So basically, it's an integer, but now if the hold would be active, then the integer value goes in and you keep it. And then when it comes time to interpret, what does it mean to say stage 1, which we'll get to, dot out? Well, that now means the 5th item, if you will, in this container somewhere, that reactor's out is the out of this expression. So that made it easy for me, and I think that's probably where I went wrong in this exercise. So the property is checked as above, but it can't be satisfied. The counterexample trace is shown for all the reactors, which of course is both necessary and potentially even more confusing. So I have this here for completeness. I'll go back to it if I need to, but let me just go forward and show you what I'm building. So this is the first thing that I put together to test out the new code that could handle this case. And I didn't expect it to be a problem. I thought it'd be fine. I hit go, and I waited. And I'm going to assume it was about an hour later. I'm sure I killed it the first few times that I ran it, but I do have numbers. And many times it runs taking an hour just to do this simple problem. And I don't have it here. I do need to show that to show it. But the bounded case in the bottom is to say that if no single update, I'll describe the updates in a bit, but if no single update is greater than or even equal to 10, then the output won't be greater than 100. But there's 3 of them. So yeah, that's totally not true. Any 2 of them, that would be true for. But once you add the 3rd one, it is possible to, say, configure it with 999. And the product of that will be big enough to violate the rule. The behavior here is that we have the input. The first stage will multiply the input by whatever it was configured with when it was created. So it starts off as just a pass-through of the input equals the output. But if we get this config input, so there's a lot of syntax I've not gone into, but if we get this config type, it is of a type that can contain 3 different cases. Effectively, it's a sum type. So 3 different cases, one for configuring stage 1, for stage 2, and stage 3. They can come in any order. But the reason I did this was to simulate the idea that they could come in any order. And honestly, the thing could configure stage 1 all 3 times. That won't violate anything. But I wanted to allow it because it seemed like the sort of thing to do. And as I said, it ended up being far slower than I would have expected. But the idea would be that if the config comes in and it matches being type config S1, then that value C will be made available to a subsequent expression that builds a stream. That is what I'm doing with the slant, is to say things that are streams. There will be a stream containing this mult, this instance. It's really just the integer pointing to where it is in that storage. That may, and in fact, whenever it's active, will arrive and stay in S1. And the fun bit is that the way that I've implemented it, if S1 is swapped first, no, that's not interesting. If S2 is swapped first, then it will depend on S1.out. If you then swapped in S1, some systems, maybe all that I'm familiar with, would actually require you to redefine S2 again because the old one you made was listening to a different object. But here, when it says that statement, S1.out, it means whatever my owner's notion of S1.out is. And so when you swap S1 out from under it, it now takes on the old value. And so this is what I was saying about everything gets to keep a name, and we no longer, or we can't end up with linked lists, which is too bad. It is a limitation on what you can do. But it does mean that you know what you're talking about and you do have a name for everything. But as I said, yeah, it took way longer than I expected, so I scaled it down and realized that, yeah, for the smaller problems, so scaling it down was a manual process of cutting out the third stage and running the same operation, but only 2 stages, and there it wouldn't exceed 10, so on and so forth. Very quick for the smallest case, and then, yeah, exponential growth, but not just exponential growth, since that's expected to a certain extent, but really slow exponential growth. And maybe I'll go a little bit into why that is, well, why I think that is. But the next thing I tried, and as far as I got for this project, was to make simpler versions. So the baseline had the S1, S2, S3 configuration type, but it put them into just some coefficient numbers. And then the output was equal to those 3 coefficients times each other and then times the input. The sequential stage insertion took away the ability to do them in arbitrary orders, and it did help, but not all that much, which is interesting. And perhaps the way I described it made it so that the Z3 solver didn't know that as many of the side paths didn't need to be explored. And that's really sort of where I am. I was going to show, at this point in the slide, there we go, on the left, that's what the counterexample trace looks like. I did, to make it slightly more readable, take the numbers and turn them into the name, effectively, of the subreactor. But when you look at that for a counterexample, what you end up seeing is that, and it just happened to do this, it swapped out S3 first. So the initial configured mult 0, which has 1 as its coefficient, still sits where it was. Mult 4, similarly, is one of the initial ones. And I'd have to scroll down to show it, and it's not terribly important, but mult 8 is just no longer being used. And maybe I should show it just because it's there, and that, I think, is the problem. I declared mult 8 and defined what it would do for the next 2 time ticks, even though, admittedly for this case, but even though it was not being used at all. And I think there's a good chance that Z3, with the properties that I've passed on to it, is trying to solve all of those, like basically all the pieces that it doesn't need to find value. It's still applying the rules. And so one of my thoughts is to basically make all the rules conditional on whether or not the thing can be pointed to, or something to that effect. And that's easy in this case, but I have not considered whether or not that's something I can do practically long term. So, pop that back up. I am running, it feels like overtime. But yeah, the goals are provide hints to the SMT solver because, yeah, this is just way too slow. It's only 3 stages. Yes, 3 stages with more variety than realistic code might have, but still 3 stages. And so my thought is that, yeah, if we could flag them somehow as just not being active and tell the SMT solver there is there's no restriction on this value, just assign whatever you want. I can't make the value not exist once I've declared it as a holder, but there you are. Or, and I don't even know if this will help at all, but place a bound on the number of subreactors so that, I'm not interested in all those 9, I think it was. Actually, it was more than 9 possible subreactors that could occur if they get swapped out at this or that time. If I basically just said, yeah, there are 3 initial ones and you can have those and then 3 more that might get swapped in, what is that going to look like? And I worry that what that will look like will actually end up being more complicated. There's a whole bunch of rules governing which one of them is active. But because it is fewer things to fill in, yeah, it's possible that it might work. What I intended to do next, assuming as I had that I would continue to get reasonable performance, was containers and some look at basically some new syntax for how to deal with containers of reactors, either pipelines like they're shown here, or probably a lot more fan in and fan out to deal with perhaps a manager of some kind that's managing a bunch of workers. And then, finally, full circle, to bring in the metric temporal logic operators that sort of what kicked the whole thing off. The cool thing is if you can put a time limit on your property, then it's a safety property because it can be disproven in a finite number of steps. It's still possible if their deadlines are too long for you to run out at the end, but if you're willing to set enough steps versus the size of the thing, you can end up with a safety property. And so, yeah, when doing this, you have to make assumptions about what the outside world is up to. But another option, and a tempting one, is to add MTL operators as a new kind of reactive operator. And so what that would mean is you'd be able to say something like, one of you asked about, if a thing transitions from false to true, a rising edge, then that might kick off, or that amongst any other number of events that could occur, would potentially kick off an expression that would become false if, let's say it's a keep alive or a debouncer. So if it keeps coming, then the thing can never go false, and that's great. But if it doesn't come within whatever the window is, then suddenly it'll go false. And so you can basically declare these timers that are related to your pieces and then turn them into signals that you'll react to. What should I say? Declarative way to define a timer. And you can end up writing your reactor to explain what it will do if the outside world's timing isn't good. And then you no longer need to, in your properties, make assumptions of what the outside world is doing. Let's see, yep, it is in fact the last of the things I plan to do. All right, like I said, I'm over time, but any questions?
Do you have an example of formula that would be difficult to interpret? You said, it's easy to find a contour example on your first slide. First example, but
I even consider that a hard one. But certainly, the one that I brought up over here. There we go. You can see, this does not matter. Let's see if we have out, there we go. So we can see that it got violated. So that's true. And that's actually easier for us than it is for the thing. But why? And why is a function of all three of them having been changed. And it doesn't matter that they changed the particular values that it changed to, but it might. And so that's where it gets really hard to figure out what to do with this. And having so many superfluous reactors, which in this case, it could be very clear that you'd say, it doesn't matter what was going on with any reactor that isn't at least in this list. But not every property is going to work that way. Sometimes one of them would have swapped in, impart a state change, and then now you can't swap it out. There is something potentially to be done with the unsatisfiable core extraction, which it's hard to get a minimal core, but the idea there would be if you have taken every declaration that was made and flagged it when you submit it to Z3, you can ask Z3, okay, you found me a problem. Basically, what set of assertions are incompatible with being correct? And it can't tell you that one of them is wrong in any way. All it can say is together they're all wrong. It also can't necessarily give you a minimal one. But the hope would be that you'd say, all right, something's gone wrong, and it has highlighted a lot of your declarations. Maybe that points you in the right direction, but it's not at all clear that it does so. So even though I did this, and I still think it's better than making people write proofs, maybe, but it's not yeah, it's not solving the problem for you automatically.
So it's not that the formula is going to be complicated, it's more than it's going to have a lot of intermediate steps on the size of the counterexample to interpret.
Yeah.
It's not that the property is necessarily complicated.
Yep, that's the runtime problem, potentially. But yes, once a counterexample has been shown, it's not at all clear how best to convey that to the user.
So I'm not super familiar with the background, so maybe my question won't be super relevant, but I'm wondering why you chose an SMT solver as the backend to kind of do the verification here, compared to, say, some bounded model checker or something like this, where they traditionally are used for checking some LTL properties. Yeah, and how the performance might compare.
So, given where I am, it is hard to justify, but my expectation was that I would use the real values in addition to the integer values. And I don't know that that means that there wouldn't be other tools that I could have chosen. But that was what drew me to it, is the possibility of more interesting theories. Alloy, especially recently, given how long this project has taken me, Alloy has gone from not doing sequential models, let's call it, to now having a version that does. And so that's now bringing Alloy much closer to what this is. I've not used that mode, so I don't know precisely how they present it, but I imagine it looks similar. But yeah, it was just, yeah, I had to choose one. Z3 has really great interfaces for doing what it does. Let me build models like that, that stream type, that it was easy to just describe this as a value that may not have a value. As well as the match expressions on the sum types. That was relatively straightforward, just move right into Z3.
Thank you for interesting talk. So in the last part of your talk, so you talking about, let's say, MTL for the, let's say, describing some real time.
It is. So I think it may be more general than that, but I'm only talking about the one that's time. Okay. So metric is the M, so metric temporal logic, and in particular, I'm used to dealing with the one that deals with intervals. I was able to monitor things that would not be complete. Yeah, that's fair. You can detect a violation of something, but when looking for all possible violations, it's possible that would not be. Yeah,
I'm just curious, why do you choose MTL instead of other kind of, so let's say, formalisms for time? So, for example, time automata or hybrid
personal
automata.
bias. You know, I ran into this problem, honestly, I feel like it was a misunderstanding of LTL, that there were some expressions that I just couldn't understand, why is this considered sufficient? And it has to do with LTL not assigning a truth value in between the points. And so then I found that there was a logic that did. And so I was like, that has an intuition for me. And I particularly like, although this makes it harder, the dense time and the continuous, continuous semantics, such that you don't get slight, I guess you'd call them paradoxes, like the idea that, so one of the operators is basically future 10 would mean something like within 10 hours, days, whatever. Future 10 is a logical expression you can state. Future 10 of P, whatever it is not necessarily equal to future of 20 of P. And if that confuses you, it should. That feels weird. And it has to do with the fact that the point-wise semantics doesn't work that way. And so, yeah, I really like the idea of the continuous. You treat them as signals. A lot of the terminology ends up being the same as FRP, which is a little bit what drew me into it. But that idea of a logical signal becomes very easy to process.
Thank you very much.
Let me change that. Easy to reason about, harder to process. It's easier if you can just basically say, I've got a finite number of events, and whatever happens, happens.
So you showed us your SMT backend. Do you already have also a runtime for your language?
No, Of all things, I know, the most fun to play with. So whenever I execute this, I can only execute it by writing something false and then watching it build me a counterexample. Yeah, that has never seemed like the hard part, but I may surprise myself there as well, that, that I may have written myself into some interesting corners.
Any other questions? Thank you very much.
In the third session of Rebels today. Is the right. Close the door. The setup is working. Should be. Perfect. Then every time. Great. Thank you everyone for being here for the third session of Rebels. I've been long involved with the workshop, and now I'm the first time session chair. And I immediately give off to talk about composability of message passing systems in a very related area. So Alfred, stage is yours.
Thank you. My name is Alfred Åkesson, and I will present Compos, a DSL for composing IoT systems with weak connectivity. This is joint work with Göral Hedin and Niklas Fors, and we all work at the Department of Computer Science at Lund University. This work was part of my PhD thesis. When programming IoT system that connects different devices, one can use scripts to mediate the messages between various components of the IoT system. We call these scripts compositions. These compositions need to account for the fact that IoT systems have weak connectivity and that connections can go up and down. If these scripts have state, one need to handle this in the presence of weak connectivity. The handling of states in these compositions will be the focus of this talk. I will now show a scenario to illustrate how state can be introduced in composition scripts and how this can lead to problems we try to address. The scenario starts with a stateless system, and we later extend it with state. Here we have two devices, a camera that is in a garden and a TV that is in a house. In this scenario, the camera is self-firing and takes a photo every 5 seconds. We want to show the images from the garden on the TV, and the interfaces for the camera and the TV is provided by the services running on the devices. To connect the camera to the TV, we write the composition scripts that mediates the photos from the camera to the TV. We consider this IT system stateless as we do not store the photo or any other state in the composition. The script does not need it because it forwards the image to the TV as soon as it gets it, and here weak connectivity will not be a big problem. An interruption in the connection between the camera, between the composition and the TV leads to lost photos. However, when the connection is restored, the system functions normally again. To extend this scenario to a stateful system, we note that at night, when it's dark in the garden, the images are just black. So there is no reason to show the photos on the TV anymore. Thus, we change the system so that the TV only shows photos when it's bright outside. Our new goal for the system is to show images from the garden on the TV if it's bright outside. We add a light sensor to filter out the dark photos and only send the images to the TV when it's bright outside. So now the camera sends a photo to the composition script. When the script receives an image from the camera, it must first ask the light sensor if it's bright outside. It can do this by sending a message to the sensor and waiting for a reply. During the wait, the compositions need to store the image, and thus it has state. The photo the composition stores is shown here. Now the composition sends a request to the light sensor, and the light sensor reply. Then, when the result from the sensor arrives, it sends the photo to the TV. In this example, we see how the photo stored in the composition adds states to the system and make it stateful. If a reply from the sensor is lost, the composition script will be stuck waiting for a reply. We need a mechanism to handle this situation so that the system is responsive, at the same time does not store a lot of data due to stuck programs. In this talk, I will present the abort semantics, a mechanism for managing state in compositions. What our abort semantic does in this scenario is that when a new message arrives, it removes the current stuck composition state and starts processing the new image. The abort semantic is designed in the context of the service composition architecture. To explain the service composition architecture, I will expand this scenario. Here we have a schematic view of the example with the services camera, TV, and light sensor, and the composition A connecting everything. We add an extra camera, and we also add an extra light sensor and the composition B, which combines the behavior of the sensors to provide a so-called synthesized service. The synthesized service allows the composition to provide an interface with the combined behavior of the light sensors. Now let's more explicitly introduce the service composition architecture. The service composition architecture has three concepts that are important for this presentation: the services, the compositions, and the devices. Services provides functionality, but don't know to whom they talk. Instead, their functionality is accessible through an interface that the compositions connect to. The composition composes the services in a system. Compositions are specified in a domain-specific language. In this talk, this language is Compos. Compositions can be used to combine multiple services into so-called synthesized services. And in this example, B combines the light sensors 1 and 2. It's through synthesized services we can connect composition with each other. Here, A connects to B via the synthesized service. The devices host the instances of the services and the compositions. A device is a running instance of the middleware software. One device in the architecture often corresponds to one physical device. So, the compositions are specified in the Compos DSL. On this slide, I will give a brief overview of Compos, and on the next slide, I will show it in an example. The Compos DSL sets up connection to the services and then coordinates outgoing and incoming messages. It has no support for computations. Instead, computations are delegated to the services. There are 4 control flow constructs in Compos: sequence for doing one thing after another, select for handling alternative responses, parallel for waiting for responses in parallel, and finish first to wait for one branch to finish. Compos is implemented on top of the Palcom middleware, and the Palcom middleware uses the service composition architecture. Here we have the system again that shows images from the garden on the TV if it is bright outside. In the middle is the Compos script, and during normal execution of the script, the camera will spontaneously send a photo. The composition will receive it, And the photo here matches the first line in the script. This is an outer when clause that waits for a message named photo sent from the service camera. When the composition receives a message that matches a when clause, it will execute the body under it. A script can have multiple outer when clauses to wait on different types of messages. When a when clause matches, it creates a reaction. A reaction is a runtime activation of the compo script, and a reaction consists of program counters and variables similar to a stack frame. Here, the program counter is shown as the arrow here, and the reaction is down here. And in this case, the reaction contains the value P, that is the photo. And the whole state of the composition is determined by the set of reactions that it has, and that is what we want to manage. The composition sends a request to the request check light to the light sensor, and now it waits for a reply here, and a composition can handle incoming messages either by resuming a reaction like here, or by creating a new reaction when we have the when clause. The reply from the light sensor arrives and the reaction resumes. Last, the script sends the picture to the TV. When a reaction is removed, all its associated states is removed as well. So by removing a reaction, we can remove a stuck composition. So we will now look at different alternatives of handling ongoing reactions when a new message arrives. Suppose there is an ongoing reaction waiting for a response from the light sensor. What should happen if a new photo message arrives? What should the composition do? We have 4 examples of strategies for handling this situation. With the ignore strategy, we ignore a new message because we already have a reaction running. With the queue strategy, we put the incoming message in a queue and wait for the current reaction to finish before starting a reaction for the next message in the queue. In parallel, we execute the 2 reactions concurrently. With the abort strategy, we abort the currently running reaction and start a reaction for a new incoming message. The abort strategy is the approach we chose. However, a naive implementation of the abort strategy could lead to some undesirable behaviors. One issue is that messages from different sources should not abort each other. For instance, if 2 cameras simultaneously send a photo to the same composition, one of the reactions will abort the other in a naive implementation. In our implementation, we want messages from different sources to not abort each other. Also, messages sent in the same reaction should not abort each other. For example, if a reaction sends 2 messages in parallel to the same synthesized service, one of the reactions at the synthesized service should not abort the other. Many similar but more complex situations can arise in network with multiple interconnected compositions. To mitigate these challenges, our implementation of the abort strategy only lets newer related messages abort a reaction. To do this, we introduce epochs, and an epoch consists of a place and a time. In our case, the place is a connection indicated by P, and the time is a counter indicated by the subscript T. We tag both reactions and messages with epoch, An incoming message with epoch pt prime aborts a currently running reaction with epoch pt if and only if they are from the same place, i.e. p prime and p are equal, and the message is newer, that is p prime is larger than t. T prime is larger than t. Now I want to show two examples to illustrate how the epochs work. For this example, we will show the example what happens in a system when camera 1 sends an image. For this example, we call the two connections from the cameras to A for strawberry and ice cream. It starts with the camera 1, which sends a message with the image of the on the connection strawberry to the composition A. When A receives the message, it creates a new reaction with the epoch strawberry 1. Reaction A sends a message to B and tag them with the epoch. Upon receiving the messages B starts a new reaction with epoch strawberry 1 and sends a request to the light sensors 1 and 2 tagged with the epoch. The light sensors measures the light and respond. B then combines the result from the light sensor 1 and 2 and replies to B. B combines the result from the light sensors by replying that it's bright if any of the sensors says that it's bright. After replying, B ends the reaction. When A gets the result from B, it sends the image to the TV and ends its reaction. In the second example, we have the same system, but the timing of the messages will be different to show the abort strategy in action. It starts like the example from before with a message from camera 1 to A. Then A sends a message to B, and B sends a message to the sensors. At this point, A and B awaits responses and can potentially be aborted. What happens now if camera 1 sends a new message? A will create a new reaction with epoch strawberry 2. This new reaction will abort the old reaction because strawberry equals strawberry and 2 is greater than 1. A will also send a request tagged with strawberry 2 to B. The message sent to B will create a new reaction that aborts the running reaction because the new epoch aborts the old. The message sent from B will now have the epoch tagged with strawberry 2. Now camera 2 sends a message on the connection we call ice cream. This message starts a new reaction with the epoch ice cream 1. Composition A now runs two reactions. They do not abort each other because they are from different places, strawberry and ice cream. Next, composition A sends a request to B tagged with epoch. B creates a new reaction and runs it in parallel. And that's the end of this example. So, to conclude the abort strategy, it removes obsolete reactions without the need for timeouts that need to be tuned, Removing reactions is important when we have weak connectivity because otherwise it's easy to accumulate a lot of obsolete reactions. The abort strategy also processes the freshest message immediately, making the system responsive. We are pretty sure that we can statically determine if a system has a bounded number of simultaneously ongoing reactions, and this is a problem we have started to work on. However, one drawback of the abort strategy is that it can be too eager and abort reaction that would have finished otherwise if one waited a little longer. For example, if the light sensors are slow and the camera takes photos quicker than they can respond, we might end up in a scenario where all reactions are aborted and nothing reaches the TV. You can find more in the paper. For example, the paper thoroughly describes Compass, describing all the constructs and the syntax. The paper also describes how other strategies like ignore, queue, or parallel can be implemented with the abort semantics by using an additional special service. In this paper, we also evaluate Compass with the abort strategy by successfully implementing 7 home automation scenarios proposed by Rodriguez Avila et al. The paper also includes a small performance evaluation using a macro benchmark, and we measured the round trip over Ethernet, and for Compass it was around 1.7 milliseconds, and in a pure Java implementation of the same composition it took 1.6 milliseconds, so the Java implementation was 5% faster. Thanks for listening, and I now welcome any questions.
We already have any questions from the audience? So, hey.
I have been a little bit lost when you have presented your language with your 4 constructs, you know, parallel, first, all these things. I am not so sure where are they executed, or which language are you describing? Is it for the green boxes or?
Yes, it's for the green boxes.
Okay, and in that part, you don't need preemption or abortion in the language itself? For instance, you could decide that you are executing things in parallel, and for any kind of reason you want to abort something or you want to kill some computation?
So the language itself does not have any computation, so to say. You just do the message passing. So it doesn't have loops and stuff.
Finish is a kind of abortion. When you receive one, you kill the others.
Yes.
So you don't feel the need that you have a dedicated construct for doing this kind of abortion. You don't need that.
No, but it may be something that would be needed.
Does the, what was it, first of abort all other than the first one?
What?
There's parallel and then something else that was first. Finished first, yeah.
Yes, but it's so if you have here we have a picture of them. So if you have finished first, you can send like a request to a service, and you send. So how this would execute is that you do the send and you do the send, and then you wait for any of them, and the one that will come first, you will not do anything here, and you will continue to execute here.
Hello. So in languages like ambient arc and E, you have this notion of a far reference. So it's a pointer over the network which points to something which is far away. and there is like hidden in the concept of the programming language level, there is a buffer that takes care of intermittent connections. Would it be fair to say that this is like kind of an algebra to combine far references? That allow you to do meta programming and make very complex very complex far references?
Yeah.
Because there you also have the notion of leasing. If you send messages over a far reference, you add a time interval, and when the time is up, the message automatically garbage collects.
Okay.
That's one of the things that you have.
So in this architecture, so my name is Boris Magnusson. I'm from the same university. Is this on? Yeah. Yep. Sorry. So if you take up one of your slides with the green and the architecture, here is, I mean, this can be used both within the same device connectivity, where it's less likely that things get lost, but it can also be used, but some of the more complicated ones. So these on the right hand side, these are far references if you talk more, but the one between the camera and A is a near reference. So if one of the things that are far, for example, some of the light sensors are lost, the connectivity, there is in the underlying architecture the notion that there is a timeout between these devices, which means that the connection is lost and everything is removed. So they're not there forever. But it's sort of a part, that is part of the architecture itself, how long timeout you want to accept. It is. Yeah, so it is in the architecture, not in. And is
it transitive if they refer to each other?
No, it's in every connectivity, so to speak. So if you and yeah, so I think that explains your question perhaps best.
Yep.
Yeah.
Questions? Then I get to ask mine, which is somewhat related. I was wondering about the parallel composition. Can you, if you parallelly compose things, mix, I guess, transactions from different origins, like strawberries and ice cream, or can you not mix them for parallel composition?
You cannot mix them because the when here is what like says this which the connection is, and then this is in the context of that epoch.
Right. Do you think that would be useful for, say, future extension of the language?
Maybe.
Very good. Any further questions? Otherwise, I think we're also good. Any next speaker can set up?
I will mirror my screen. So.
Right, I guess we're...
Dislikes.
I guess the next speaker that is currently set up is Philip from the Hasso-Plattner Institute, talking about Arctics, which, as far as I knew, is a Rust actor framework, and seemingly it previously didn't have any capability for remote connectivity, which is interesting choice for an actor framework. But I guess this has been fixed now. The talk has not quite yet been fixed, but
Yes. I guess so.
now it's how it should be.
Yeah.
Great. Then the stage is yours. Please go ahead.
Thank you. Yeah, I'm Philip. I'm from the HPI in Potsdam, Germany, and I created Actix Telepathy, which, as already introduced, is an extension to the Actix actor model library, so that you can have remote actors and build distributed systems in the actor model itself. So my actual research is something completely different. I'm a researcher in anomaly detection on time series, and last year we created with other people of my chair a large evaluation where we used about 150 algorithms. So we implemented these and tested them on a lot of benchmarks, around 1,000 data sets. And we found out that many of these algorithms are either qualitatively bad or they have lots of timeout and out-of-memory errors when the data sets grow large. And therefore we thought to ourselves, we need a technology if we want to also build algorithms in this case that has certain requirements and is able to analyze all these big data sets. And the three requirements that we had were they should be resource efficient because we don't want these errors to happen for our algorithms as well. Reactive, obviously, that's why I'm here in this workshop, so that they can adapt to the data and the different distributed parts can talk to each other. And it also should fit in the Python environment because most of these algorithms are written in Python. The benchmark setups, benchmark libraries are also Python, and so we wanted it to be integrated. And one language that popped up that was suitable for us was the Rust language. It's memory efficient, quite fast in comparison to Python, and it's also easy to integrate into Python. So you can port it to, so you can create Python libraries out of Rust binaries and frameworks. And the problem was that the actor model libraries don't have these remoting features. I think I don't have to explain what the actor model is in this context, so I will just skip over these slides and jump right to this one here. So these are the current the largest in terms of downloads actor model libraries that we found for Rust. The biggest one, this logarithmic here, the y-axis. The largest one is Actix, with at the moment these numbers are from this week, almost 6 million downloads, and then the second largest is 110,000 downloads, and then it gets lower, yeah. And so we said, okay, let's go with the Actix library. None of these libraries support a remoting feature, so they all run local. Let's go with the Actix library. So now I'm going to introduce to you how you can build some very small basic applications in Actix itself. So it all starts with importing the Actix library itself. Then you create, in this example, an actor that has a state which is a positive integer number called myActor, and you implement an actor trait for this actor so that it acts as an actor and can receive messages. Each actor has a started method, which is called once the actor has started. So in this case, this actor, if it, once it starts, prints out that it has started. My actor started here in green. Then you would create a message. In this case, it's called my message, and has some these yellow lines above it are macros. So the first one will implement a message trait for this struct, and the second one defines what the return type is. But in all these examples, there are no return types. That's why they are empty. And then you would implement a handler for this message for the already created actor, where you would also define the result, which is empty, and the actual function that is called once the message arrives. That's the handle function. In that case, the actor would print out that it has received this message, but also this the position where it would update its state based on the messages that arrive. And you start the application by creating this actor, starting the actor. You receive the actor address, and then to this address you can send messages. And in the end we have a sleeping function so that we can wait until the message arrives. Right, so once you start the application, it will print out that the actor has started, and then the system sending a message to it, and the next printout line would be the message is received. So the structure of this application looks like this. There's a message, an actor receiving a message from the system, basically. Then, in the second example, we will create a second actor, which we call my second actor. And as its attribute, it has the address of another actor that can receive my message. This actor will then print out that it has started once it starts, sends a message to the address it has as an attribute, and tells the user that the message has been sent. Starting the application would look like this. You start my actor, you receive the address, and then you add the address to the second actor, start this actor, and wait for 3 seconds so that everything finishes. The output of this application would then, as expected, be similar to the other one, where you have an actor that starts and receives a message now from the second actor that knows its address. But now the question arises: so if we have now the setup that one actor should be on a different computer than the other actor, we would like to have a remoting feature, and that is not supported by Actix. That's why we created this with the telepathy extension. And an example would then look like this. The goal of this library was that it should be easy to switch from one library, from the base Actix to our extension. And so the only thing you have to do in theory is that's the same code as the one before, but now we have these two macros, these yellow lines above my actor, where we are defining my actor to be a remote actor, and define the messages that are received over the network, so remote messages. And the remote message then, we replace the macros of the Actix library with remote message, and also it has to be serialized and deserializable. And now the actor is able to receive this my message over the network, and the message handler stays the same. So this would be then easy to implement if you already know the Actix library. And now the problem is, once you start the application, you don't have the remote address of the other actor on the other computer. That's why we cannot tell the second actor from the beginning that this is its recipient here, the address. So we have to find a way around this, and this is happening by listening to cluster events. So there's a trait called cluster listener, which we will implement for the second actor, and a handler that's listening to cluster logs. This is an internal behavior of the telepathy application. So you can, any actor can subscribe itself to listen to cluster events. In that case, once a cluster node joins the cluster, an event log is sent to in this case, my second actor, which can either be a log saying there's a new member as we see here, or a member has left, which in that case doesn't do anything. But in the first case, the new member has arrived. We get the node that arrived with attributes like the IP address and some utility functions like get remote address. So in that case, in this line, the my second actor would receive the remote address of the my actor on the newly joined cluster node, and can then send the same way as in the usual actix behavior a message to this remote address. So this would then be the main function that would start everything. We start my second actor, we start my actor, and then we start a new cluster. Give it the own address where it's listening to incoming requests, and some seed nodes so it can connect to other nodes in the network. The application would then do something like this. We have so basically we have both actors on both systems, and once the cluster connects both nodes together, the my second actor receives the remote address from the my actor from the other system, and then will send the message. And I hope I can just jump out of here to show you the like a very small demo. Yeah. So we have one node on the left here, and we have another node on the other side. The left node starts on the port 1992, the other one on the port 1993, and the right one takes 1992 as a seed node, so it knows where to connect. And when we start the left one, it says that its actors has started and it's not doing anything. And then once we start the right one, it says, okay, my message is received. So it connected and then got the address from the other node and sent a message. And that one also received a message because they do basically the same. Right, let's jump back in. The architecture of the actix telepathy library looks like this. We have a cluster node, a cluster actor. These are system actors. A cluster actor and the gossip actor. The gossip actor is sending the new members that are joining the network the addresses of all the other members that are already joined in the cluster. Network interfaces are created once a new member joins in the cluster. So for each member, each system has a network interface to the other members. And then there's also this address resolver, which is handling the forwarding of incoming messages to the right actor on the local system. Then we have a remote actor trait, as I've already shown in the derived macro, and a remote address. These are these new kind of objects that are floating around in the telepathy system. And once you send a message from one actor to the other, the dashed line shows that it knows the address. So the actor on the bottom right will internally send a message to its network interface connected to the network interface of the other machine. This one sends this message to the address resolver with the recipient name, and the address resolver then knows where to forward this message to the actual recipient. This all happens in the background, so the user does not have to know this kind of behavior, as I've shown in the examples. And this all happens when you say this function on the lower left, do send this message. We did some benchmarking experiments here compared it with Akka and Orléans, since these are like the big actor models from other programming languages. And in this example, we had a distributed application that is searching for prime numbers in a range 0 to 100 million. And the x-axis shows the distribution, so how many nodes participated in this cluster. So here's 100. No, right, yeah. And the y-axis is milliseconds. And as you can see, Actix telepathy scales in a similar way to Akka and Orléans. And since Akka is running on the virtual machine, we also ran 2 different versions with restricted memory. So we measured the memory used by Actix telepathy and then restricted the Akka system to this amount of memory, and then it only goes until 10 nodes, and then it stops because it runs out of memory, also with extra buffer. In another experiment, which we call Power Ping Pong, are 2 nodes that are sending messages back and forth, and with each sending, it doubles the size of the message to see that in this case, we want to show that the serialization and all this message forwarding does not affect the performance in a negative way. And here we also see that it's right in between Akka and Orléans. And in the last experiment, we actually had this use case from the beginning. So we wanted to use it for building a distributed time series anomaly detection algorithm. And one particular algorithm that is finding anomalies in time series called series to graph. What this one is doing, just briefly, it looks at the time series, spins it around a geometric origin, and then builds a graph out of this geometric representation. And out of this graph, it can read which parts of the time series are anomalous and which are not. And a master student of ours distributed this algorithm in Akka. In our experiment, we then implemented it in Actix telepathy, and then could nicely compare it here. And as we can see, Actix telepathy actually scales very well with the number of nodes, up to 120. And Akka from, let's say around 60 nodes, has a larger communication overhead, and so the runtime increases then again until it stops because it doesn't communicate anymore if you have too many nodes in the network. Right. And so we actually then extended this algorithm even further to run it on larger data sets, and it's at the moment under review at the ICDE. So let's see what comes out of this. Right, and that's basically my story using the actor model libraries. This whole project is open source. You can find it on the left QR code. This is my university website. And with that, I'm open to questions. Thank you.
Thank you very much. Are there any questions? Because I have one first. What happened to Erlang?
You mean in terms of benchmarking? Yeah, we didn't use it.
Any particular reason, or just because
so we
had to make selection?
Yeah, so one reason why we didn't use it is the problem with all these anomaly detection algorithm libraries is they use some stuff where you need other libraries doing data science and this and that, right? And so with it was already quite hard to build an application like this with Java, I have to say, and Orléans. So yeah.
So it's about the remaining ecosystem.
Exactly. Yeah, we wouldn't use it. Yeah.
Questions?
Okay, thanks for nice talk. I'm just curious about this architecture diagram. So how do you manage the remote references? Do you do some kind of distributed garbage collection or something?
Sorry.
distributed garbage collection was?
No, the garbage collection is done by Rust, and so the internal structures, there are open TCP channels between these network interfaces, and so this is then also handling the heartbeats and everything that's internal. So we didn't have to implement this, and right, yeah. But the garbage collection is done by Rust, and
yeah, I'm just yeah. My question is about remote references. So remote reference should be kept when the how to say the target object is arriving. So that,
okay. So the remote references are implemented the following. I hope you can still hear. These network interfaces exist for each connected node. So when you have one machine and this is connected to 3 other machines, then this one machine has 3 network interfaces. And so if it wants to send a message to one of these 3 machines, it goes over this network interface that is connected to this machine that has an open TCP channel, and in this message is wrapped in an object that holds the message, the serialized message itself, and an actor ID, which the actor ID is like this local address, and this is translated by the address resolver. So the network interface receives a message, unpacks it, deserializes the message itself, looks at the actor ID, and then the address resolver is forwarding it based on the actor ID.
Okay, thank you.
So do you allow actor references to be passed as arguments of messages to other actor references?
Yes, but they don't work. so you can okay. That was the question.
The garbage collector.
Yeah. No.
You have a spaghetti of references.
Exactly. No, that doesn't work. So because the local addresses are basically addresses on the memory saying this actor, but this doesn't work remotely here.
I have a slightly related question, which is about the ownership type system and what interaction it has with the actor model. Like, is this a positive interaction? Do you not notice any insights?
The Rust ownership, you mean? There are some problems. So I said that I don't use the message response, right? So the message response was always empty. The problem here was that if you wanted to have a message response, then the ownership and the whole actic structure doesn't really allow it. So you would need to hack your way around, and yeah, that was too ugly. So I said no, I want to have the clean implementation distributed, and then.
So you would say the ownership type system is not, let's say not at least not now well compatible with the actor model, at least not in the remoting case.
Not in that particular case that I encountered. But.
And does the remoting make it worse than local actics, or is it already a problem in just actics?
So I encountered this problem only in the response, in this remote response feature that I didn't implement in the end. But in the rest, it's fine because it's super isolated, since you are working with these handlers and they're very isolated functions which do not access other features. Yeah.
Further questions from the audience? Because I do have one last one,
yep.
Which is related to your last point. So you added basically new API surface for some remoting features, like getting remote references from the nodes. Did you have to adapt anything at all from the like the just actor API surface, or does what actors has work just fine even for the remote case?
Yeah, I didn't change actics. Okay. Yeah, it's 2 libraries you implement. They have to.
So basically, I guess what I'm saying is the programming model remains exactly the same.
Yes.
For the remote case.
Yeah. That was the goal of the. Yeah.
Maybe one final. Maybe you mentioned it. I don't know. So what happens if an actor explodes? You have a heartbeat.
Yeah.
The other ones get notified. Do they have to clean up their reference tables and stuff like that?
An exception happens, right?
And then?
And then there are some structures and ethics around this. So you can have actors that are watching different actors, and once these actors fail, they can be restarted. They get notified, but this is already implemented in ethics itself.
So that's like spawn link in.
Right,
in
and so if the TCP channel somehow disconnects, then the network interface fails, and then the cluster is notified. Yeah.
Great. I guess then let's thank the speaker again.
Thank you.
And we can have the third and last talk of the session. I guess we're nearly ready to set up. Well, we're nearly finished with setting up. This will be Daichi from Oita University, and we'll get the latest and greatest on persistent signals. This time implemented in a environment that allows it to be even more widely used than before. Daichi, the stage is yours. Please go ahead.
My name is Daichi Hidaka from Oita University. I will talk about my joint work with Tetsuo Kamina. The purpose of this research is realize persistent time-varying value in JavaScript. A persistent signal is a signal that has a history attached to it to enable access to past values. In the next slide, I will explain about them. We illustrate this purpose using a simple IoT device monitoring system that mirrors the output of a fan controller system in a browser. It switches the state of the fan between on and off according to the monitor discomfort index. This discomfort index is calculated using values obtained from temperature and humidity sensors. All these values are persistent time-varying values. The system outputs them to the browser. It also provides the time-traveling feature using a slide bar. One convenient language feature to construct such an application is signals. A signal is an abstraction of time-varying values. Unlike ordinary variables, signals do not require explicit reassignment. And when the value changes, the dependent value is recalculated. Thus, the value of b in the following code is initially 10, but with signal, the value of b automatically becomes 12 after the value of a is updated by the increment of a. This allows for simple handling of data flow linkage. Signal.j provides persistent signals, which permanently stores signals in a database to enable reference to past values. This is suitable for handling of time series data, which is one of the features of IoT systems. As an example, The code on the right requires the vehicle signal class for a vehicle tracking system. This class requires two persistent signals, X and Y, that represent the position of the vehicle. The modifier persistent is used to require persistent signals. Last if and distance methods calculate their change amount and the velocity of the vehicle. In signal J, each persistent signal is given an identifier, and by referencing the ID, data stored in the database can be referenced as a time-varying value. In the code below, by providing ID OITA 1234 to the instantiation of the vehicle class, the signal associated with the identifier can be obtained. When you want to refer to past value of the signal, persistent signal, we can use the snapshot method to access them. As an example, the vehicle signal class can be used to refer to the velocity of a vehicle at time t using the code below left. First, the snapshot method sets the timestamp to specify the time. It then sets the time cursor of the instance. Then we can refer to the velocity at time t. In this way, persistent signal provides the time traveling features. The network between persistent signal forms a location transparent distributed data flow. This distribution is made possible by the ID resolution server, which stores the ID and the corresponding database access information. The Signal J program firstly finds the database using the ID by querying the ID resolution server. Then access the database to use the persistent time-varying values. There are two problems in implementing persistent signal in JavaScript. That is, the web front-end application has the browser limitation. And we need to consider the reuse of the existing JavaScript ecosystem. First, we need to realize the seamless connection between time series database and JavaScript programs. We still preserve location transparency of persistent signals. In addition, we would like to use the existing JavaScript ecosystem in implementing the persistent signals in JavaScript. So we need to implement persistent signals without extending the JavaScript syntax. To tackle these problems, we propose a deployment of Relay server to enable communication between JavaScript programs running in the browser and the time series database, and introducing a DSL library to realize persistent signals without extending the JavaScript syntax. These slides show the overall architecture of this study. This architecture consists of a relay server, a DSL library, an ID resolution server, and a time series database corresponding to each persistent signal. Our architecture provides a relay server that mediates communication between the browser and the database. Assuming that most JavaScript applications use Node.js on the server side, this relay server is pre-populated as a template in the Node.js project and is implicitly started when the Node server starts running. Communication between the browser and the relay server is established using the WebSocket mechanism. When a persistent signal is instantiated in the browser, a connection request to the relay server is sent to the Node server. The relay server then communicates with the ID resolution server to connect the time series database. After the connection is established, the relay server mediates bi-directional communication between the database and the browser. Next, we will discuss the relay server. The persistent signal requires an access to the database that runs on a remote server. But libraries for connecting to the database are basically not available in the browser. So we introduce a relay server to enable communication between the browser and the database. The relay server mechanism is explained using the diagram below. First, the browser sends a connection request to the Node server when an instance of the persistent signal is created. This request connections the ID of the persistent signal. When the relay server receives an ID sent by the browser, it finds the database information from the ID resolution server. The ID resolution server returns the access information of the time series database, such as its URL to the relay server. The relay server then establishes a connection to the time series database based on the information received. This enables communication between the browser and the time series database. Finally, relay server sends the data obtained from the database to the browser. The relay server also keeps the signal values on the browser updated. When the time series database is updated, the database immediately notifies the browser of this update. For example, when a value in the time series database is updated, other than by a browser operation, the time series database immediately notifies the relay server of this update. This relay server listens for this notification and, upon receipt, notifies the browser and triggers browser re-rendering using the updated values. This re-rendering is performed implicitly by the TSL library. In order to realize persistent signals without extending the JavaScript syntax, the persistent signal mechanism is realized as a JavaScript DSL library. The signal class provides the functionality of signals, and the signal class encapsulates the persistent signals that form the data flow. The pSignal class provides the functionality of persistent signals and actually communicate with the relay server from this class. The figure on the right is a class diagram showing the relationship between these three classes. One of the functions of the signal class is the extension of the persistent pSignal class, which is performed in the constructor of the signal class. For example, the following code is an example of the fan controller system. The instance of temperature, humidity, and discomfort index are created using signal class with the user-provided ID. These instances contain their own persistent signals, and when the instances are created, they are connected to the database identifier by the ID. The constructor takes an ID and the name of the persistent signal. The constructor then internally creates an instance of the persistent signal. The signal class provides pSignal encapsulation and time-traveling functions. Access to the persistent signal is only available from the fields of a signal class instance. For example, the latest values of temperature, humidity, and discomfort index are accessed as the persistent signals, which are fields of signal class instances. Finally, the time-traveling function is provided, which sets the time of a persistent signal using a timestamp. For example, the monitoring system provides the time-traveling function. This is achieved by connecting a slide bar with a call to the snapshot method. This challenge of the slide bar triggers calls of a snapshot on each signal class instance to change its timestamp. The time-traveling feature is explained using the following sequence diagram. Communication to the relay server starts when an instance of the persistent signal is created. More precisely, a WebSocket-based connection request is sent to the relay server. This initiates communication with the relay server. When the timestamp is set in the signal class instance using a snapshot method, a data request at the timestamp is sent to the relay server using the JSON format. The relay server then accesses to the database and obtains the value of the persistent signal at the specified timestamp. Finally, the pSignal instance received the values from the relay server and renders the browser to display the received data. As related work, I introduce other JavaScript frameworks that support reactive programming. First, React provides a similar mechanism to signals that allows for automatic computation. Next, RxJS provides a function similar to the signals in the study, but it is known to cause glitches and it's not strictly based on FRP. Flapjacks provides two language constructs, event and behavior, which abstract time-varying values in the FRP language. The difference between this research and related research is the avoidance of glitches in distributed persistent signals using timestamps. In summary, this study provides a JavaScript implementation of the persistent signals, which are formally implemented only in Signal.j. For this purpose, we propose a deployment of relay server that relates communication between the browser and the database, and introducing a DSL library that provides persistent time-varying values functionality. One of the challenges for the future is that the DSL library is not able to create new persistent signals. At present, signal class instance are mirrors of existing persistent signal instances. We are planning an extension of the signal class to generate new persistent signals from the DSL library. This is the end of my talk. Thank you very much.
Questions from the audience now that the mic is working. So I have one initial question, which is about the your future work, I guess. How do you currently how do the persistent signals currently get the values into the database? Is this like built into the core language, or do you use some other system? Like how does that look like?
Oh, okay. This slide.
So I'm wondering about how, because you have sensors, right? And somehow the sensor data gets into the time series database.
And
I'm wondering, like, is that just hand implemented, or is there some like more generic mechanism you want to just make available in the language, or what are your more concrete plans there?
I beg your pardon. One more time.
With any other questions from the audience? Speaking of this slide you have here, I was wondering, because you've selected a very classical architecture, right, with the front end, a server application, and a database. Have you thought about other architectures, or why specifically choose this architecture for this use case?
Oh, yeah. Because browser and time series database connection enable. We need relay server.
So that the database side, so for persistency, also we require the time series database. So that's the reason why we use the database. I'm not sure your question. So did I answer your question?
So I understand why you use the time series database, right? Because you want to store data in there, they come from the census. That makes sense. But why specifically then this classical web architecture? I see that if you want to make it available in a browser, you may need this relay server. That's fine, but the relay server seems to also do some logic, right? But you could, for example, also choose a different architecture where you had like some peer-to-peer communication between two nodes, doing the data there, or something else. I was just wondering why, in particular for this IoT use case, this traditional client-server architecture was the right choice.
So first of all, we assume that there is some data source. So using the existing data source, we would like to, provide some combination of the in a declarative manner. So this is our the first motivation. So did I answer the question?
Any further questions from the audience? If not, I guess we can thank the speaker again.
Thank you.
And this has been the last talk in the session as far as the program is concerned.
Yeah, and in addition to the last talk, it was also the last session. So I thank you all for showing up for this day for Rebels. And maybe Wolf, you want to add some few words?
Okay, so maybe you don't know me, I'm Wolfgang de Meuter. Together with Guido Salvaneschi, we created this workshop. Actually, this was the 10th edition. And so I also would like to thank Manuel Serrano for playing the role of the PC chair. So Guido and I, we are still in touch, and the idea is we have a sort of a steering committee, but it's more like, it's a big name for nothing. The only thing we do is just submit the proposal every year, make sure we have a slot for Rebels, and then we try to find a PC chair to make sure that the academic content is independent from me and Guido, and otherwise it would be the Wolf and Guido workshop, and that's not the goal. So if you would be interested in being next year's PC chair, or you know someone that would be a good PC chair, drop us a line. One thing that I noticed is that until a couple of years ago, we had a competing workshop, was Agere, and it sort of was a very similar crowd. People sometimes were switching back and forth between the two tracks. And I know that the Agere workshop died a little bit, maybe not because of shortage of interest, but just because people left the university and didn't want to do the work anymore. So one option, but this is just a proposal to the community, I don't want to decide anything, just let me know, would be to maybe organize something like a joint Rebels and Agere workshop, and to reactivate that crowd, because I remember like every year we had like a couple of papers, maybe not enough to fill an entire day, and they had the same problem, yes, at Agere. But at the same time, I think the community is not dead, because every time at Rebels we have like 20 people in the room, so people are clearly interested in this topic. So maybe we should just like join forces and with the actor people next year, and make like one interesting day full of actors and reactors, maybe with 2 PC chairs or whatever. So if you have any thoughts on this, just send me or Guido an email, and we will do the rest. So, thank you.
Okay. Thank you, Wolf, and thank you for everything.